the end.
Can you flip them to the center screen, or what am I doing? I just see them in a little teeny box and see the solar catalog
Yes.
on the big screen.
How do we give control?
Or just make them the center screen?
Yeah. There, perhaps I will stop sharing my screen. How do I do that?
Yay.
There they are. Great, thanks.
Thank you.
We're just pulling up our PowerPoint now.
Wonderful. We can see the whole PowerPoint, get it into the presentation, and begin when you are ready.
Thank you so much. So we are from the University of New Hampshire, and we are competing in the residential new housing division.
So for the location of our home, we decided to go with the site at 176 Stage Road in Nottingham, New Hampshire. It's a 4.5 acre lot that is all cleared with 600 feet of river access. It has great views and it's located in a quiet area. So for the exterior of our home, we are going with durable vinyl siding as well as double pane windows to allow for plenty of passive solar. Keeping that in mind, we have 3.5 foot overhangs over all windows to allow plenty of light in the winter while blocking out light in the summer. We also have steel doors that are both durable and energy efficient, as well as metal roofs that allow snow and rainfall to slide off due to our climate. We also have rolling window shutters on all windows in order to create a better thermal barrier. Keeping that in mind, we did a snapshot of the heat gain and heat loss during the month of March. And we found that we actually had a net heat gain of 37,900 BTU per day. Additionally, some members of our team decided to go a step further and do a physical test to confirm our use of our double pane windows by testing the heat transfer through a single, double, and triple pane window. So for the interior of our home, we have a semi-open concept that is 3,000 total square feet with 2,660 square feet of living space. We're going to have dark flooring throughout the home to allow us to trap a lot of that heat in during the winter. And we will also have a minimum of 32-inch doorways and an ADA compliant lift system in order to make our home completely ADA accessible. Throughout our home, we're going to use a cloud MIS smart home technology system that is all smartphone accessible, so it's easy as a push of a button. We will also have Honeywell IAQ.2 thermostats throughout the home to help us regulate temperature as well as monitor CO2 and VOC system temperature values.
In terms of the structural system, we wanted to select design and material options that adhere to the Nottingham IEC codes. These included double stud framing and raised heel trusses made with engineered lumber, where the treated wood would better withstand the environment as well as loading. For the mechanical systems, we wanted to build those based off the structural design. These included plumbing, electrical, and heating and cooling. Specifically for heating and cooling, we wanted to opt for the geothermal ground source heat pump. And for the electrical system, we wanted to utilize photovoltaic technology where we source our solar panels from local solar energy companies. To take advantage of the passive solar energy, double pane windows significantly minimize the heat loss overnight. The option between interior sliding or exterior rolling thermal shutters allow freedom of aesthetic choice as well as automation and control in the smart home.
For our target market, we chose to use the typical American family, just 2 adults and up to 2 children. We chose a target home cost of $500,000 because based upon our numbers, we found that that was roughly the same as the town and the county. We also wanted to leave enough room in the budget to incorporate our zero carbon systems.
In terms of durability and resilience, we found that the biggest threats to our area were floods, winter storms, and high winds. We decided to choose a location at a high elevation to prevent flooding, and also chose durable materials to prevent damage from wind and snowfall.
In terms of embodied environmental impact, we want to choose materials that are mostly carbon neutral, such as timber, in terms of the structural components of the home. In terms of the mechanical systems, we want to choose low carbon systems that also will have long service lives as long as 20 years. Thirdly, we also, one of the pros is that the area we chose to build a home is in a pre-clear lot, and it also has an existing road next to it, meaning that all the environmental disturbance will be kept to a minimum while building the home. And lastly, we also chose materials for the structural mechanical components of the home that will have minimal waste generation at the end of their component life.
In terms of integrating performance, we chose double stud walls, which allowed us to choose a smaller geothermal heat pump and therefore less solar panels because we needed less electricity. This allowed the cost of the home to go down while keeping the reliability up. We also are prepared for a New Hampshire climate, specifically snow and rainfall. We chose the angled metal roof to keep snow from piling up, and also a rainwater collection system that can reuse that water for irrigation on the property. As previously mentioned, we chose a forced air heating and cooling system with the geothermal heat pump. This allows us to connect it with the smart home technology and therefore change the amount of heating and cooling used throughout the house at different times of the day and week, depending upon who's home. For lighting, we also chose recessed lighting along with the windows. We plan on putting LED light bulbs in each room with different temperatures dependent upon the purpose of the room. And we also are using overhangs and landscaping all around the house to choose the amount of passive solar going into the home so that we get more light and heat in during the winter and less during the summer.
When we were designing this home, we desired to make one that was open for people of all abilities, from the most athletic to people suffering from temporary injuries to people with long-term injuries. We also desired to choose a location that was fit for working and also relaxing to make sure that this home was desirable for people to live in.
In terms of the geothermal for the house, we chose a GeoComfort PSVT system. This is a closed loop system, so it circulates antifreeze rather than water, which needs to be drained with an open loop system. We chose a 5-ton heat pump based on the square footage of the house, and we're using ground source heat pump because it's more efficient in the winter and it's less noisy and requires less maintenance than an air source heat pump. We also are incorporating vent fans and makeup air units within the house to assist with filtration. We also have entry ramps into all entrances of the home with that overhang that was previously mentioned to prevent snowfall from covering the ramps. In terms of the solar panels on the house, we're utilizing 44 panels at a 36-degree roof angle. This is a 19.8 kilowatt system size, which is based on the rated power output from the panels, along with the number of panels that we are using. As you can see from the chart on the left, the production from the panels outweighs the consumption from the house for most months out of the year, except for November, December, and January. In these times, we'll be using renewable energy sources from the grid to help power the home. However, in the months when we are overproducing, we are able to put that energy back into the grid. We are also using a battery system on the house, which can be used in an emergency scenario to distribute power to necessary components of the house. So finally, based on DOE information from our area, we found that the average yearly consumption or average yearly generation for flat plate solar panels for our area is about 28,000 kilowatt hours per year. We also found that our house will consume about 22,000 kilowatt hours. So based on this, without accounting for solar power, we found a HERS score of about 38. However, with accounting for both the solar power and the geothermal, we found a HERS score of -19.
Thank you very
Thank you.
much. Yeah, you hit your 8 minutes perfectly. That is exceptionally well done.
Thank you.
Jurors, do you have anything you would like to ask?
Yeah, I can jump in really quick. So I think good job on pairing. I heard you talking about pairing the envelope with the mechanical system. So making the envelope more robust so that you're reducing the size of your mechanical system, which is a geothermal and forced air system. So I think that's a good approach. I was curious about, you mentioned and showed your analysis of double pane windows and triple pane windows, seeing that the triple pane windows were performing very well in comparison to the double pane. I was wondering why, what made you make that choice for the double pane?
So the reason that we did that was because we wanted to use enough passive solar to help heat the home in the winter. And we ultimately felt that if we use a triple pane window, it wouldn't let in enough sunlight during the winter. So that's why we went with the double pane window.
Sue, I think you're muted.
Hi. I guess my question is more on the renewable energy side. It seems like 20 kilowatts is a whole bunch of solar. And even for a 3,000 square foot house. But did you look at the window to wall ratio on there? And then you have the R value of your foundation as 1. Is that really 1, or should it be 10 or 20? And that's why you got such a negative HERS rating at the end. Does your utility buy back your electricity at retail or wholesale, or why are you over doing the solar, I guess?
Brooke, could you talk about the solar and then Jess can talk about the foundation?
Yeah, so we are overproducing on the solar. We have a sort of large house, under 3,000 square foot. However, in the winter, we're underperforming with the solar. So we wanted to kind of make up for that underperformance by overperforming a little bit in the years, or in the time of year when you might generate more power. So we wanted to try and get our underperforming months, so November, December, January, to be as close to being able to actually power the house as possible.
I live in a geothermal solar house, so I love the technology. It's wonderful, but
And
I
then-
don't. Your utility rates really determine whether you want to go and overpower it in the summertime. If they're only buying it back at retail, it's probably not worth it to you.
And then just to touch on the foundation aspect, we utilized the Ecotrope software that was provided by the Solar Decathlon. And one of the aspects for the foundation walls and for the, I think, freight slabs of the home, we opted for the XPS slab. And the default for that was an R value of 1. And then also researching it up online, we were finding just sources that were consistently telling us that it was an R value of 1, even when doing the thermal evaluation of the thermal envelope of the home.
So could you put more insulation on the slab and maybe optimize the window?
Absolutely. So the slab was something that we were struggling with because we wanted to opt for concrete at first, but then realized for cost reasons, XPS was a better option. And in our next iteration for the design, the slab and foundation of the home is something to definitely focus on, considering that other families might want to opt for a basement, or whether or not they're just satisfied with the 2 floors above grade.
Thank you.
A quick question about material use. So you had mentioned steel doors. So I was curious about just climate wise and why steel doors, and then the consideration for indoor air quality for material use inside, I think it's again very smart. But also you had just mentioned vinyl siding. So just wanting to get some more background on why choosing vinyl siding for the exterior, and then also steel doors and not maybe an insulated door.
So we kind of just felt that the steel doors were a fairly good insulator from the research that I was able to conduct. And we also saw that steel doors have very low carbon emissions. So we were ultimately focusing a lot on trying to create that low carbon emission when building a house.
And in terms of the vinyl siding, our focus was to try to design a home that would be affordable. And so we're trying to stick with materials that were commonly used. definitely, I believe there are other materials out there that could fit the affordability and better for the environment than vinyl siding. So looking into the future, I think that is something that we should review and consider changing.
Thank you very much. That's all the time we have.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks, University of New Hampshire. Next, we have up Wentworth Institute of Technology.
Hello, everyone. Let me share my screen. Hello, we are Wentworth Institute of Technology's new housing group. I'm Chrysula. I'm Lexi.
I'm Mason. I'm Ben.
And for our detached housing proposal, we've designed 2 separate buildings located on one site with the potential for future projects to be mirrored later. Our site is located in Cambridge, Massachusetts. Our design goals are to create a net positive environment or system for not only our project, but also for future proposals and projects, and to inspire the city of Cambridge to collaborate and build while thinking about the future buildings and communities in a sustainable environment.
So we achieve these goals for net positive design through strategies including capturing solar energy using a geothermal heating and cooling system, including a rainwater collection and gray water system, and by using sustainable building materials.
So looking at Cambridge, it's a progressive town that understands the need for emerging technologies and sustainability. The city spent several years planning the initiative called Resilient Cambridge to reduce the risk of potentially devastating storms and floods and to mitigate rising temperatures.
So our site is located at 851 Cambridge Street in Inman Square, which is an incredibly dense neighborhood relative to the rest of Cambridge. This 0.18 square mile area has a population of over 12,000 with an average household size of 4.4, whereas Cambridge as a whole has an average household size of 2.2. Our site is directly across the street from the King Open and Cambridge Street Upper Schools, making this a prime location for families. So as we take a closer look at the site, we can see that we've divided a large site in halves and quarters, activating only half of the site for this project with preparation for using the rest of the plot to mirror the design that we created in the future.
For precedent, we looked at the TH House in Vietnam by Odo Architects. This was designed to maximize the amount of daylighting and communication within the space.
Now, taking a look at our project overall, you can see the relationship between these 2 single-family homes and the portion of the plot that they take up. So some passive and active strategies we used. Passive, we designed sun shading devices on the south-facing windows, included vacuum sealed windows to limit heat transfer. We've designed roof rain drains in the collection garden and lifted the foundation for flood prevention. Active and strategies include capturing energy with solar panels, using a shared geothermal system for heating and cooling, which will be run from the power generated from the panels, and a gray water system.
Taking a look at a rendering from the entrance space, this shows the relationship between the both buildings and creating chances for occupants to interact with them.
So looking at the plans, we intended to have an open floor plan on the first floor of the homes to allow for flexible uses of the space, as well as to let daylight into as many areas as possible. The front house has 3 bedrooms and the back house has 4.
And now taking a look at this section, you can see the extra floor height given to the back building to maximize the amount of natural light that they'll receive.
In the facades, we can start to see the materiality, specifically the Shusugibon siding that we chose. The treatment of the wood allows for minimal upkeep and makes it incredibly resilient to fire, past UV, and can even absorb impurities in the air.
The U.S. Department of Energy is also funding to award $300,000 to $13 million for projects to help communities design and deploy geothermal district heating and cooling systems. Considering this system, it will provide energy for 2 existing units as well as potential units developed in the site. Here we compare traditional Western framing styles with Swedish framing. The traditional framing styles leave 6 to 7 thermal bridges, while the Swedish framing style that we chose only leaves 2 thermal bridges. We chose rigid cork insulation because it is renewable, sustainable, and recyclable. We also chose vacuum insulated windows. That is a better option in the life cycle analysis. Roof metal system, metal roof helps the heat island effect in the city with less emissions, better SRI, and cost savings because it lasts for 200 years. This roof makes a support surface for mounting our solar panels while allowing for ventilation to the panels and roof.
For interior materials, we chose to use ceramic kitchen tiles, which are highly sustainable from natural clay and are easily produced, recycled, and maintained without the use of toxic chemicals. And softwood flooring as renewable, also softwood flooring as a renewable resource, and is both cost-effective and versatile.
So looking at material locations that we chose, we attempted to choose materials that are manufactured relatively close to the site, with most of the materials coming from the Eastern United States. The exception to this is the rigid cork insulation, which is grown and manufactured in Portugal, but we felt that this was the best material choice due to its thermal conductivity, acoustic properties, and ability to resist moisture, on top of the fact that it's fully natural and renewable resource. The homes are in a fantastic neighborhood for community engagement with many small businesses, schools, libraries, and parks within a short walking distance. And our design also equips each unit with bike storage areas to promote alternative transportation to driving, which also encourages families to engage with their neighborhood.
Here we see how shading systems are helping sunlight get into the building when it is needed and how it helps the building stay cool during the summer.
For solar panels, we use the Prism Solar 445 watt power performance panels, which test above and beyond the IEC standards. And we're using iron gate mounting system to mount the panels onto our metal roofing.
The solar panels provide twice the amount of energy used in the buildings annually, putting the rest back into the grid. By analyzing our systems, we can see that the life cycle performance has a positive effect on energy efficiency and embodied carbon emissions.
Now looking at flooding as a major issue in Cambridge and Boston. The average sea level in Boston Harbor is expected to rise steadily in the coming decades, doubling every 20 years. Several dams are at risk to cause significant damage in many local communities. We've implemented a rainwater collection system that'll return the water for use in the landscaping, laundry, and plumbing, and end up saving a great amount of municipal potable water. We've also lifted the foundation 5 feet above the street level to help when it comes to the storm surges. So the average cost per square foot for the project is $183, which is within the typical range for new builds in the area. The average rent in this area is $3,800 a month for 830 square feet, with 65% of homes being renter occupied and 35% being owner occupied. So the cost for this build is a worthwhile investment. Looking at the bigger picture, a geothermal district heating system could help towns and cities achieve a measure of energy independence, giving a reliable source of heating and cooling that never changes price and requires no imports. Geothermal energy can significantly contribute to cut US emissions in half by 2030 and achieve a carbon-free electric sector by 2035.
And future projects are able to plug in to their central shared geothermal system with the design perfect for mirroring.
Thank you.
Thank you.
Thank you very much, Wentworth Institute of Technology. Back to our jurors.
I live in a geothermal house and I love it, but the drilling costs are usually super high. Have you looked at the difference between, did you look at air source heat pumps? I know there's a lot of new money out there for geo, but, and then any microgrids or sharing between these two houses?
Yeah, so both houses, and in the future, if both houses were mirrored, so all 4 houses would be connected to the same grid, so it would be sharing.
The school across the street has a geothermal system. Yes, drilling is incredibly expensive, but I'm sure the grant could cover it. To cover the costs of energy for all 4 of these sites, we would need maybe 9 6-inch diameter holes drilled at 1,500 feet. We didn't exactly do the calculations on that, but I think it was under 6 or 7 million, and the grant provides 13 at max. Considering Boston's how far we would have to drill down to get to hot water, or at least 60-degree water, 55-degree water, it'd be 1,500 feet. So we wouldn't be able to do anything other than drill.
I had a question about the resilient strategy and the flood map. So I didn't see your, okay, your site is here. So how high will the foundation be raised?
5 feet.
5 feet, okay.
I'm trying to figure out how you get to construction costs less than other houses in Cambridge. You have like such wonderful technology, and I love the architecture and the design, but it seems like it would be far more expensive. Where's the cost savings come from?
Yeah, we have done a lot of research into different grants and like tax exemptions and stuff like that. So like when it comes to the solar panels, we found like a tax credit to take off 22% of the solar panel system. With a lot of the choices that we made sure that the reason either the cost would be cut down because of a grant, or the cost would be worth it in the life cycle analysis for the upkeep of this home, and also like the protection that it gives for like these storm surges and the future heat rising.
I will note that the geothermal system is not included in the overall cost, so I'm sure that would have made a drastic difference.
Yeah.
But as Priscilla said, it is specifically in that portion, we were considering that there are like really good grants available for those systems.
Are you including the cost of the land? It seemed,
No.
okay, yeah, that's,
No, that I'm sure that would be huge.
yeah, you need to put that in there to really.
Yeah, okay.
Apples to apples.
Okay.
Can you talk a little bit more about, you did a comparison between Swedish framing style and kind of your envelope strategy. Would you talk a little bit more about that in terms of insulation values and air sealing?
So the insulation value, you can see how thick the Swedish framing is. We have about 10 inches in total in Swedish insulation. So if we're doing cork, the R value of cork is about 3.6 to 4.2. We'll put it right in the middle. 10 inches, we get R value of 38 plus the slight amount of R value, the siding and the frame gets us, I'd say 38 R value in total. And if we want to talk about the thermal barrier or thermal gaps, the only thermal gap we see on the Swedish framing is up near the roof and foundation, and because the floors are also insulated.
Yes, since the insulation goes into the floorboards, it makes it much better when it comes to thermal bridges. And you can see here that the vapor and retarder goes all the way down through the foundation, where in typical Western framing, it stops before it's all sealed up.
Mm-hmm.
Thank you very much. That's as much time as we have.
Thank you.
Thank you.
Thank you, great project.
Yes. Thank you, Wentworth. Up next, we have Oklahoma State University. Anybody from Oklahoma?
They're probably over on my link.
Yes, certainly. Wow. Yeah. Well, I think we don't have them now. We'll move on to the next team, and hopefully we can find them perhaps after the break or before the break. Then we can watch that team. That brings us to Appalachian State University. I know it's jumping the gun for you guys. Appalachia State, are you close to ready?
How's it going? Yeah, we're about ready. We just gotta get the camera lined up and ready, and then we'll be good to roll.
Yes. So we see you, we do not see your presentation yet.
Gotcha. How about now?
Not yet. There's the presentation.
Fantastic.
All right. Well, whenever you're ready and our jurors are ready, Appalachian State, you're welcome to begin.
All right. Thank you so much. Well, hello, thank you for the introduction. We are Appalachian State, and here is our affordable new housing solution. The name of our project is Applique, which is a stitching technique in which small sections of fabric are weaved together to form a larger image. Here is a brief overview of our agenda, as we will be stitching away through our presentation. So our team at Appalachian State is very interdisciplinary. Students have backgrounds in interior design, architectural technology and design, construction management, and sustainable building system. So moving on to Watauga County as a whole, despite being in the southern United States, Watauga County is cold and wet. The climate zone distinction of 5A is actually the same as Buffalo, New York. Another complication is the price of land and houses. Median home costs have skyrocketed in recent years, pricing out almost all families in the area. Which is why, to combat this issue, we are partnering with the Watauga County Housing Trust. The organization uses a 99-year land lease model, which has had success in other areas of the state, to provide a cost-effective solution to the shortage of developable land. Moving on to our site, this is the site in which we'll be building, located a convenient distance from campus. It currently is owned by the county, and who is also very interested in creating a pocket neighborhood to combat the affordable housing crisis. So moving on to our concept, which is the Appalachian quilt, which is a fantastic embodiment of stitching together panels to create something greater than the sum of its parts. Reflected in our concept are the project goals that have guided us throughout every step of this process. Sense of place, making sure that every house feels like a home. Flexibility, ensuring the house adapts to the client and not vice versa. Equitability, providing a safe and comfortable environment at an affordable price. And sustainability, reducing our footprint by as much as possible. Without further ado, here is our new housing project. The occupant experience, the designs are customizable to adapt to a variety of occupants and their evolving programmatic needs over time, such as growing families or as financing allows. The designs are centered around a volumetric wet core paired with a block scheme for reconfigurations, supporting the goal of sense of place. The ADU, or accessory dwelling unit, provides flexibility to the occupants because it can be utilized as additional living or rented out for additional income.
For market cost analysis, recently land prices in the housing market in Boone have been a growing issue in the community, people trying to buy homes and afford to live in the area. Along with vacation homes in the area for tourists to travel to Boone every year, is a tough housing market to find and be able to afford a home for a reasonable price that some households can afford. Our housing project is going to create homes in an affordable price range for different families who live and work in Boone. We are still comparing different types and forms of panelized building methods, and this graph is an example of how we are comparing these different methods. So we made a commitment to use panelized designs such as SIPs versus stick built as an example, but we are still developing our building type to figure out the best panel design for our application.
So as for architecture, the base plan can be modified to allow for a second story option, as well as two schemes that expand on the first floor. This can add an additional bedroom, an additional bathroom, a dining room, and an expansion of the kitchen. Each setting and design really showcases the surrounding view of the site, all the beautiful views.
For engineering, we had an idea to create a central volumetric wet module to include all of our systems and plumbing in the home to one wall that keeps it all in a central area. We also took inspiration from B Public and their panel design approach to create a grid design for our own building panel system that would enable us to create many different house options and for our home to be flexible. The whole system is tightly insulated with the floors, walls, and roof panels being insulated and a truss style roof on top to cap the building.
For the durability and resistance of our structure, we know the envelope and materials of our system must be suitable for our climate zone 5A in the mountains of North Carolina. As we narrow in our choice of panelized assembly, hydrothermal analysis through roofing will play in a prominent role.
The final decision will come down to a balance of thermal performance, moisture management, cost, and constructability. The integrated performance section of this project is a really exciting one for me. We're utilizing the panelization approach for most of the building, but we found that there may be some real opportunity using a volumetric wet core to achieve meaningful cost savings at scale. Now, one of the challenges there is to make sure that we have enough space for all the distribution systems in this small compact volume. It's really important to us to make sure that we get the right amount of air to each bedroom and private space with the minimal amount of ductwork beyond the volumetric wet core. That's the challenge at hand, and we're having a great time exploring all the possibilities. In the terms of systems, we're utilizing inductive mini split, an HRV, and heat pump water heater. As for the energy performance, we are using performance-based design by bringing in energy modeling early in the process, evaluating orientation and window to wall ratios and how that impacts the HERS rating and necessary roof area for photovoltaics. This helps the team really tune up and refine the panelization approach and window locations for this building. If we decide that the building location is not suitable for photovoltaics, we're evaluating community-based solar solution to zero out our energy.
As far as comfort and environmental quality go, to ensure a safe indoor environment, we're going to be going above and beyond to achieve EPA Indoor Air Plus certification. We'll also be using all Energy Star appliances and meet the WaterSense certification requirement to conserve two vital resources, energy and water. In terms of embodied environmental impact, to minimize Applique's footprint, we are using a cradle-to-cradle approach, expanding the scope of sustainability from raw material acquisition to deconstruction and reuse. To ensure net zero carbon, we will be focusing on areas that matter most, producing more energy than consumed through PVs and making conscious choices about material selection will have the greatest effect on reducing our environmental impact. Here's our project timeline. We've done a lot so far, but there's still plenty more to do. And in summary, Applique is our unique approach on affordable housing in the form of a pocket neighborhood. We achieved our goal of sense of place by making families feel safe, secure, and seen. Flexibility through customizable layouts chosen by the client. Equitability by providing low-cost construction methods, zero operating costs, and an additional revenue stream. And sustainability through smart material choice and on-site renewable energy. We achieved our goals as a result of our innovations. The wet core, a volumetric prefab system that centralizes and controls utilities while keeping installation costs low, and the ADU offers space and economic flexibility through a detached space that can also be rented out to offset the majority of the mortgage cost. Thank you guys so much for your time.
Thank you very much, Appalachia State. You even managed to get in under 8 minutes. To our jurors, what would you like to ask?
Yeah, I have some questions. I think that generally the flexibility and the panelized system, I think it's very creative. In the next phase, can you talk a little bit more about what you would want to do with the flexibility? Would you want to be applying this to one site and seeing kind of test running it and do kind of a prototype of your system approach? Can you talk a little bit more about that?
Yeah, I mean, I certainly think we always want to be thinking about the building in space. So really focusing in on the site, doing further analysis as far as solar path, illuminance values, and really having that flexibility allows us to conform to our site in the most efficient way possible. And having as many different configurations will get the best energy and occupant experience for the clients.
When I read your write-up last night, I was thinking this is like the perfect template for every housing authority. You know, you got all the good parts to it. You've got, you know, an ADU, you've got panelized systems, you've got the core or wet wall. These are just all the best practices in sustainable building. So that's really great. And then I was like, but it's all theory, like you don't have any, is there a project behind this? And then you showed the project. So I applaud you that you have the site, and it would be really great to see this built and see, you know, how it works out in your community.
Thank you very much. I mean, we really are looking for this to explore as a solution in our site, including the fundraising and building. So we're really taking this seriously as if it was a project that we hopefully will actually be able to build.
Yeah, I think that the partnership between you and the county, the housing trust, could you talk a little bit more about that? I know you mentioned it's a land lease solution. And I just think we get excited when there is kind of more of a partnership. It really does kind of make a more reality-based project. So yeah, could you talk a little bit more about that and how you came to them or they came to you?
Yeah, absolutely. They kind of actually really caught wind of us as a result of the IDEX lab program that we used to have, which now transitioned into the Solar Decathlon Independent Experience. The Appalachian State is really tied into the community. We have faculty members who are on the board of the Housing Trust for both the county and the site. And so really they wanted to involve the students in the solution to really lead the change and lead that way. And all of the utility, all of the resources that we have here, both in the university and the faculty. So they reached out to us, we came up with the design plan, and a lot of our faculty are involved in the logistics of the Housing Trust, working with ordinances in the local government, as well as the fundraising with local businesses. We really want this to be a solution made by the Appalachian region for the Appalachian region.
I love your sense of place and community. I served on a housing authority for many years, and it was always about just build a box and stick people in it. You know, having the views and having community and having, you know, creates a quality of life that people can go and thrive in. So that was really awesome.
Anything further from the jurors?
Get it built.
That's our plan. We're gonna get it built.
Yes, we're very interested to see all of these projects get turned into real life.
Good job.
Yeah.
Thank
Thank you so much.
Thank you very much. For the rest of us, we will take a 6-minute break until the next presenters, Oklahoma State, will have joined us, and they will begin at 12:55 Eastern Standard Time. Please enjoy a few minutes rest. Hello, everyone. It is time to resume. Is Oklahoma State prepared?
Yes, we are.
Marvelous.
Here.
Marvelous. Yeah, get your slides ready. And good to see our jurors are here. Yes, the recording is going. So Oklahoma State, begin when you are ready.
All right, hello, we are Renewable Orange Power from Stillwater, Oklahoma, participating in the U.S. Department of Energy Solar Decathlon. Our team consists of students from Oklahoma State University, including interior designers, mechanical engineers, a construction manager, and an architect. We are excited to partner with Habitat for Humanity Stillwater to design a home that is not only zero energy, but is also cost effective and helps families in need. By choosing this unique partner, we face the challenges of meeting the needs and requirements for both Habitat for Humanity and the Solar Decathlon. The home we are designing is aimed to help low-income families who undergo the process of being selected to purchase a Habitat for Humanity built home. Habitat for Humanity homes are constructed primarily by volunteers, and large sums of materials are donated from local businesses so that the homes are more cost-effective. The house sizes vary, but the home we are designing can house anywhere from 5 to 7 occupants.
So with our design partnership with Habitat for Humanity, it's very important that we keep cost in mind while also designing a very efficient zero energy home. So the size of home we're building is a 4-bedroom, 2-bath house at 1,400 square feet. Now, a normal Habitat for Humanity home built in Stillwater, they aim for about $100 per square foot. So with our added technology and efficiency, we're aiming to increase that price just a little bit up to $140 a square foot. We're aiming for a HERS score before renewable energy generation of 45 or less. Right now, we're sitting at about a 44, and we're seeking to lower that further. One key constraint for our design is that we have amateur labor building a home, which is what Habitat for Humanity utilizes. And so one crucial design element is that we have to have a simple construction design. And so that shows itself in having a simple structure, a simple roof line that's all familiar to Habitat for Humanity. Another way we can do this is by keeping our plumbing and electrical simple. And then as we go into this building design, we also have codes that constrain us in that. So the base code for Oklahoma is IRC 2018. And so that's just our basis, but then we also refer to IECC as well as ASHRAE 90.2 to get some more efficiency requirements to set a baseline of where we need to design our house and then go from there. So going to our site, this is our location. On the right, you'll see a satellite image of where this is going. So this Habitat for Humanity home will also be part of a larger neighborhood that Habitat for Humanity is building. So if you see on the left side, there's an image of the neighborhood that will be being built. So it'll be about 14 houses. The house we're designing is in the bottom right corner there. So as you can see, a big emphasis here will be the community aspect of this neighborhood. So with our location in Oklahoma, we also have climate considerations. We sit in climate zone 3A. We have summers that can get into the triple digits and winters that can get into the negatives. So we have a lot of extremes. On average, our highest temperature in the summer is about 93 degrees on average, and then our lows in the winter are about 23 degrees Fahrenheit. So with our location, it also impacts our durability and environmental impact. So one big emphasis here is our building envelope. Our environment that we're working in and our temperature conditions definitely inform how we design our envelope. So one thing that we have in our design is that most of the exterior of the house will be vinyl siding, but we'll do the bottom third with brick on the outside. This will add a design aesthetic to the house while also providing much needed durability and longevity for the home. Within our walls, we're looking at doing fiberglass batting between wood studs, using continuous insulation with a rigid foam board, while also maintaining our air and vapor barriers. Also crucial to our design is the embodied carbon and how that impacts the environment. We have to balance between using materials that at the start of building may have a higher embodied carbon, but they are going to last longer. So we seek to find a balance there. One unique opportunity we have when working with Habitat for Humanity is to utilize recycled materials. Habitat for Humanity has an extensive network to be able to do this, and we can use materials that would otherwise be thrown away and use them in our design in the build of the house. It's also crucial to use locally sourced materials and choose materials for longevity to decrease how often they have to be replaced.
So diving into our floor plan, the facade faces north and the front entry enters into an open concept living area and kitchen. The master bedroom is directly off of those two spaces, being efficient for parental access to those common areas. The east side of the plan has 3 standard bedrooms with 1 full guest bathroom that has enough space for those occupants to share. The utility space that contains the washer and dryer, as well as the storage closet, is right next to the back door on the east side of the plan. A few things to point out on this plan to bring us closer to zero energy goal is the windows that were strategically placed on the north and south sides of the house, and the shared plumbing wall between the 2 bathrooms, and lastly, the plumbing remaining on the interior walls. And on the left here, you can see some 2 renderings that we've been working on. So looking further with the dimension plan, the 4-bed, 2-bath home totals to a little bit over 1,400 square feet. We designed this house with aging in place in mind. So with the master bedroom being equipped with a roll-in shower and the kitchen and layout being flexible to furniture changes or layout changes.
So on the mechanical side of things, for HVAC, we have an air source heat pump, hoods on the microwave for range. The bathrooms are being vented through the ceiling, and the dryer is sitting on an exterior wall. For the plumbing, we have a centralized plumbing system and a hybrid hot water heater. For the electrical systems, we plan to have micro inverters installed on the back of each panel so that if one panel is obstructed, the others are still able to produce power.
we're gonna have 26 panels at 365 watts each, producing a power of about 15 kilowatt hours a year. In Cove Tour, we went in and modeled a house with very baseline systems and got an EUI value of 36.04 as shown on the left side of the left image. And then we went in and put in our own design decisions and got an EUI of 1.17, including our renewable systems shown on the left side of the right image. For the final submission, the tasks are still split across the different teams. The teams stay in constant contact through a communication platform with in-person meetings throughout the week. And we will also continue consulting with our project mentors and professionals. Moving forward, our steps include analyzing equipment systems, finalizing the building envelope, and forming energy modeling. And that wraps up our presentation, and we're now open to questions.
Thank you very much, Oklahoma State. Jurors, what would you like to know?
Great, thanks. So it looks like you're putting a 15 kilowatt system on the house. Is that overproducing, or do we?
I got 9.5.
9.5.
What do they have?
Yeah, if you go back a slide, the system is set right now for 15 kilowatt hours a year. And that will,
but how many kilowatts?
Yeah.
How many kilowatts?
That's 26 panels at 365 watts, which I calculated at.
It's about 9.5 kilowatts.
9.5, yeah.
Yes, 9.5 kilowatts on the DC side.
Gotcha.
That's a pretty huge system for a 1,400 square foot house. What could you do on the energy efficiency side to bring down the size of the solar?
So that solar array right now is on the high end for sure. So that's our initial idea of where to start. So we may shrink that size down. We haven't fully performed our energy modeling to see exactly how much energy we're going to require. So this is just a ballpark estimate for right now. So as we reduce our electricity cost, I think we certainly have several methods to do that.
And what would be your top two?
I think one large area is utilizing the hot water hybrid system. So using a hybrid between a tank and a heat pump system has a large impact on electricity usage. One other area, Maddie, do you have?
Yeah. So we also haven't finalized our building envelope completely yet. And so once we get that with our envelope complete, that should also give us a better idea of how efficient our systems and electrical are going to be. And so hopefully we can lower the amount of solar we're needing to bring in while still remaining at a really low PERS rating in UI.
Yeah, it seems like you will overproduce, or, like Sue said, it's a fairly small house. And so, yeah, it'd be interesting for us to understand the envelope investment. So, tightening up the envelope, or adding more insulation, or a number of things to then kind of counterbalance that with the mechanical system and the demand that you would have for the house.
Yeah, I'd go after your wall insulation and your foundation and your window to wall ratio there. You could save yourself a lot of upfront costs. And another thing is, I wouldn't increase, you're increasing the cost from $100 a square foot to $140 a square foot. That's a 40% increase in cost. That's huge. So I'm sure you can make a sustainable house. If you talk to Sam Rashkins at the DOE, he thinks you can build a DOE zero energy home for about 6%, maybe more. So if you could really lower these costs significantly, even with solar.
Thank you for that input.
Yeah, and you had mentioned this is a partnership between Habitat for Humanity, and so the amateur labor portion of this is part of your, the build concept. So how do you intend to, how are you thinking about that in terms of buildability?
Yes, one major aspect of that is how we design the roof lines. We only do a single pitch on there. So that keeps it fairly standard. It's also standard pitch angle as well. And then also using simpler, the way we design our building envelope is still fairly standard. And so how we utilize that also helps with that reliability.
Instead of doing spray foam installation, the volunteers and like amateur labor can do the fiberglass batting, but not necessarily the spray foam. So that's why we went with that design decision.
And there's a lot less VOC off gassing with bat insulation, and so there's a lot of positives to it.
And you do have, you said continuous exterior insulation too. Is that part of your envelope? Yeah.
Yes.
Yeah. And that can be installed fairly easily by amateur labor too.
Thank you very much. That's our time.
All right. Thank you so much for your time.
Thank you. Good project.
Thank you.
Yes, and Sue, that was an excellent point for future teams when we're doing the question and answer. If you're not showing anything on your slides, we'd love to please stop sharing your screen so we can see the whole team. The jurors like to know who they're talking to.
Or I don't know if it's coming from your side or from their side. Do you both have the ability to switch between so that we could see their faces? Or
yeah,
and so I can see if Sam's getting ready to talk and I'm ready to talk, or it would just be easier to.
Yes. All right. We will see what we can do to make that happen.
Thank you.
Up next, Navajo Technical University.
Yeah, hello. All right, let me share the screen.
Good. Excellent.
Nope. I think I'm showing the wrong screen.
Yeah, we can see your notes on the side.
Yeah. No, I'm just missing it.
You have an extremely compelling story. I love this. Your reasoning.
Let me just share the screen. Okay, so we close this.
There we go.
All right, so my name is Shaquille Coho. I'm part of the Navajo Tech University team. I'm actually the team lead, one of the team leads. So my team consists of 4 electrical engineers and a couple of computer engineers and construction techs. As you know, Navajo Tech actually has trades here, so we're able to outreach to different departments. Yeah, but a majority of our team is actually electrical engineers. So what I'll be talking about is design goal, architecture, energy design, and finance. So as you know, the design goal mainly is to improve living condition, affordability, and durability. The main target market is the Navajo Nation. As you know, a lot of the houses here have been built centuries ago. The image on the right, it actually shows houses. That's actually my grandmother's house, and she still lives in it to this day. But as you know, we want to improve housing designs again, as the Navajo Nation only uses a certain housing design. So that's what the main goal of this project was. So The location we have chosen is Crown Point, New Mexico. On the right, you'll see a little plot. That used to be the boarding school building, but they tore it down, and now it's just an empty plot that sits there. So I think it'll be a really great place to actually build houses there. You could probably fit a good amount of houses there to make a nice housing with our design. So as you know, Crown Point is a small little area in the reservation that we actually don't really depend on water brought in. We actually have our own groundwater system. So a lot of our stuff is local wise. So as you know, Crown Point is actually a really desert area. We do get wind, we do get snow and rain, but our main area is wind. We get a lot of wind. Our winds can go maybe 30 miles an hour to 40, depending on the day. Like 2 days ago, it was like 30 miles an hour and it was snowing and dusty. And it's really, really bad out here some days. Yeah, and the biggest area is just our electric comes and goes because our electric lines. And yeah, so that's our main area, is just the wind. So the design we have built is a simple. We want to keep everything simple because a lot of Native Americans don't really have good housing. Most of them have trailers, RVs, or the house I showed you. So we want to actually make a simple house with 2 bedrooms, nice and easy, simple, people can get in and out of. Not too big, not too small, enough to fit a small family. So as you can see, our house design right here is very simple. And we want to actually have skylights to actually help warm the houses during the winter. And plus it brings more lighting during the summer too. So people have more lighting instead of depending on electric. So these results are coming from the New Mexico standard, local average utility cost and the carbon emission. But in reality is most Navajo houses actually don't use electricity. Most of us still use wood burners, pellet stoves. So we still use those kind of stuff. So the local average utility cost is kind of iffy because as for me, I think my highest bill was about at least $100, and it's just this year during the winter. So I don't really spend that much on the utilities. So during the summer times, I could be maybe $60, yeah, for utilities. So our HER rating is 57, and we want to try to lower that just a little bit. Now, besides designing a house, we actually want to design off-grid systems. Because the Navajo Nation actually doesn't really have electric lines that go out to a far outreach in the Navajo Nation. As you can see, these 2 house examples are actually in the middle of nowhere and we can't run electric lines to them. So what we've been doing nowadays is actually designing solar panels and wind turbines to power houses. So our design is actually 18 PV model, each of them are at 32 watts. So we actually design our own off-grid systems to to power these houses. And we do work with the Navajo Tribal Utility Authority sometimes with projects like this, since we're electrical engineers and our main focus is actually energy-based systems. So we kind of dabble here and there with them, helping them design stuff. So here's a little design we actually made for one of those housings. It's a little project that put on a rack, and we designed a battery system, inverters. We set up everything and calculated ourselves. So what we're trying to do is actually see if we can get these houses here and design it off a solar grid, a big solar grid, so we can power them without the, how would I say, electric lines from different companies. Because as you know, most of our electric comes from out of county. So we want to see if we can internally get off grid completely and make our own electric system here on the Navajo Nation. So that's our main focus here in this project. So here in New Mexico, it doesn't really cost that much to actually build a house. So it's really cheap. So $6 per square feet. So I think our main area is cost of labor. We do have to hire out of source housing designers. They got to build it themselves because I don't think the Navajo Nation is actually fit to build houses at this at this rate. And a lot of our plumbing and electrics actually has got to be built from square one, since we're going to be designing our own housing systems. So yeah, I know it's kind of short, but that's pretty much all I have for you guys for today. Any questions?
Thank you very much, Shaquille. Yeah, let's talk to the jurors.
Yeah, so just a question. So the PV module that you're building out, the kind of this battery grid bank, you said it was 18 PV modules. So is that, what are you finding? Is that powering, you said you don't use a lot of electricity in your house right now, but what would that allow you to do? Would that be multiple houses? Is that a kind of a district system, or?
So we just want to design it for this one house, because yeah, because the Navajo Nation, we don't really have much stuff. Like our internet's bad, or we don't really have nice electronic stuff, so we don't really dabble on electronics as much as in this area. So it doesn't really cost us much to design a electric for our systems. Yeah. Sorry.
I think there's something with the math that's not correct here. 18 panels at 320 is about 5.7 kilowatts. And not
Yeah. So
or it might be
we actually,
kilowatt hours.
yeah, we actually ran the numbers again and we saw it and we're like, oh no, we made a mistake. I'm like, we already submitted it. So I'm like, oh man. So also I wanted to see who's gonna see that mistake right there. Yeah, so that was kind of our bad, but we kind of submitted it too late. So I was like, oh, we can't change it. But yeah, we know.
Okay. So what if you put in more insulation in your walls, since the building costs are cheap, maybe putting some investment in the envelope would be better than the investment in solar?
Oh yeah, definitely. Yeah. Only thing is, like I said, mainly it's just we have problems with the wind, and I'm trying to figure out like how can we design a wall to withstand keep the wind out, the windows, everything. So we have a lot of different ways to prevent the wind from coming into the house and making it cold during the winter times. Yeah.
So for this challenge, you had to be down to a HERS rating of 45 before solar, and you're still up at 57.
Yeah.
So you really got to work on that envelope a whole bunch.
Oh yeah, definitely, yeah. Yeah, the main thing was we were trying to include the construction tech to help us out. Yeah, but we have a lot of projects this year, and a lot of our students are actually busy with that. That's the reason why I'm the only one here, because a lot of our students are working on other student projects, and I was the only one here to present. Yeah.
Yeah, what about in the summer? So you mentioned pellet stoves in the winter, kind of for heating, cooling. Is that just cross ventilation, or how does or opening window, or how is that?
Yeah, it's mainly just windows opening.
Yeah,
because we still I don't even know if we even use ACs. I don't even use AC in their summer. I just have a fan going most of the time, but that does cost electric, keeping it constant going. So, yeah.
Yeah, even just looking at window placement, it's a small, skinny house, right? So kind of low windows, high windows, kind of getting a little bit of you can get some convection going on in the space. So your fan is just more efficient, I guess, with pulling air in.
And what about heat pumps? They would work both as an air conditioner and as a heater?
Oh, really?
Yeah. It's just like a refrigerator. You just run it backwards when you want to go the opposite direction.
Oh, nice. Yeah. Because I was looking at the students earlier, they had that thermal underground system. And I was like, that's really interesting. I'm like, I might look into that too. Because I wonder if we could do that here in Crown Point. But I probably had to do some research to figure that out. Yeah.
Geothermal is a lot cheaper when you're doing horizontal instead of vertical, and you got plenty of land to do the horizontal.
Yeah, because I saw those two presentations. Like, wow, that actually is interesting. So I might look into that, see what we can find out here.
And that, to Sue's point, the air-to-air heat pumps, they do make some fairly small ones, especially, they're, I guess in tonnage, it's 3/4 tons, so less than a ton. And if that envelope gets, fairly tightened up, then that could be a good size for a house footprint like that.
Yeah, for your size, you want to go with the air source heat pump. A Geo's gonna still be way too.
Okay.
Yeah.
All right.
And I would add some more windows and, that connection to the exterior and the environment, and try to, that sense of place thing is really important. Especially
yeah.
design it so that, people have some central community area to play ball or trees or.
Oh, yeah. That's
Thank
why I
you
kind of
very
like going to
much.
these events. They have information. Oh, yeah. Thank you.
Thank you, Shaquille. Great, great to see building in the desert like that. We've got a minute or two for Ball State to prepare themselves, and then we will go on a 25-minute break. So.
Share.
You hear us all right?
It's a little quiet.
A little quiet, all right.
We don't see your screen yet either. It's just all black.
Okay. With that. Maybe it's this.
Oh, you think it's the.
We can see your mouse.
Okay.
All against a pure black background.
Interesting, okay. Wait, desktop, try that, maybe.
One second.
Just stop the share.
Yeah. I think it's this right here.
Yeah, should be.
Can you see that? Or it's loading?
Go to the first page.
Supposed to be the green. Why is it not? Why is it not working? No.
Try moving it to the desktop. Maybe you shouldn't share it from the extra screen either.
I think I know what's going on.
What is it?
Share the screen, not just that particular.
Oh, yeah, do that.
Okay. One more second.
Just, yeah. And then move it over. You see it now?
It's still black. It's still black.
It is still black. Why is it doing that? What?
Use drivers.
Yeah.
Okay. Use the link that you gave me.
Sorry. Me either.
6.
Oh, it seems like your computer doesn't allow.
You can use mine.
Yeah.
Okay.
It says
Alright.
participants can now see my screen. But
So,
yeah.
we gotta switch the Zoom over there.
See, I'm
Oh,
link.
gosh.
Yeah. Make sure you turn off the sleeping. Just. All right, Joe. Is it on?
Yeah, it's on.
Okay, I'll sign out of that so we can use this.
You have to get out of that one.
Okay, we have a new computer, so. Here.
Okay. Can you hear us all right?
Yeah. We need to switch it over.
It's just turn it on. Can you turn the PDF?
It's open. It's right here. It's open. You just have to launch it. Did you get out of it? Okay. Now share your screen. The PDF?
Yes, just the PDF.
Okay.
Well, actually, it's
And then
wait, which button to?
There you go.
We can now see your
can see it.
presentation, but we cannot see the presenters.
Awesome. How can I show the presenters?
Just turn on the but yeah.
Okay.
Well, his doesn't have a camera,
Okay.
so let's just use your camera.
Yeah.
All right.
Can you hear and see it fine?
You have a little feedback. Try muting or turning off the speakers to both of your computers.
Yeah.
Hello?
Yeah, there we go.
Great.
Okay. All right.
All right, Ball State, please begin.
Hello, we are the Cardinal Architects from Ball State University, and our project is called The Twin. This is a duplex style house with 2 identical units, each with 2 bedrooms and 1 bathroom in a 1.5 story style layout. Throughout our design, we had 4 goals in mind to guide our design process. One being adaptable, as in we want to design this house so that multiple types of families can live in this space equally and use it to the best of their advantage. Affordable for our context of the Muncie area. We want this place to be affordable for most families to use as they need. Modular, so that this design could be easily replicated and duplicated on multiple sites throughout Muncie to fill in the infill housing need of our community. And eco-friendly, since this is a decathlon, we wanted to have a design that had more thought put into it through our passive and active systems to make it more energy efficient and good design.
Oh my goodness.
Okay. So our site is located in Muncie, Indiana. Our climate zone is 5A, meaning that we have hot and humid summers and very cold and dry winters, making it very difficult to design for. Muncie is a city around 65,000 people, and it is most known for being a post-industrial city that throughout the 1900s was booming, but moving into the 2000s has been in a steady decline. If we take a look at our vicinity map, you can see our site is located next to the White River and just north of downtown Muncie. Keeping that in mind, we have parks and schools in close walking distance, making this a very walkable and bikeable area with a score of 81. Located in the center of downtown is the Muncie Public Transportation Hub. So all the bus routes in and out of Muncie go through there, meaning that it is easy to get around at a small scale and a large scale. If we look at our site plan now, our site is located in the red box on East North Street and North Jefferson Street. One unique characteristic of our site is that we have 2 alleyways coming in contact with our site, making it very easy to access. And we plan on using that further into our design. Muncie being a post-industrial city, the neighborhood is very low income. And it is full of 1- and 2-story homes that more and more have become vacant over the past years. And the city is doing a great job of tearing those down and leaving a lot of empty parcels. So the green areas on the map there show just at a small area right next to our site of potential infill plots of land that we could use our design and replicate it on those sites. So this is a great idea to revitalize the neighborhood along with bringing more people to the downtown area.
So throughout our design, at the very beginning, we already went into some climate and some micro and macro climate analysis systems such as Cove Tool and Climate Consultant to get a better idea of what our climate in this area and what kind of designs would work best for our environment. With the parcel of land that we have chosen, we have a very narrow north and south facades versus our very wide east and west facades, which is posing a problem for us in terms of sizing our passive and active systems, as well as our roof design, which you can see on the left. We have some iterations we went through, but we settled on this middle design that you see here, where through initial studies, we figured out that we have a very nice area in the middle of the raised middle roof there for some PV systems that can get us a lot of energy for on-site production and get us pretty much all the energy we need for typical runnings of this design so far. And on the right, you have the EOR that we have right now, which we're still working on refining to get that down. Plus with our PV systems, I think we're at a very good starting spot for getting this more efficient.
So the overall envelope shares a typical 1.5 story gable roof of that fits in the rest of the neighborhood from the eye level. There are 2 porches on either north or south side of each unit, so the occupants can decide how they want to share the 2 outdoor areas. The reason why our project is called a twin is because the 2 units are completely identical and rotated 180 degrees off of each other. The lot provides a flex space that could be used as an office space, a workout space, or even a bedroom with slight modification, promoting our goal of adaptation. The change in ceiling height created by the loft and a custom partition wall made of common wood type function as the division between the open living space at the front of the unit and more of a private living space in the back of the unit. Using custom wood pieces provide a unique look for the project while keeping the budget low.
And here on the left, you see some of our initial system diagrams. We went with since our climate is sort of harsh towards passive systems, we had to use passive and active systems in tandem in order to get a very efficient home here. For our passive systems, we realized that a stack ventilation system is one of the most effective and efficient ways of ventilating our space in our climate. So as you see, we have our loft space. Our plan is to ventilate air from the bottom living space up and exhaust through our loft to get a good natural airflow going. And in terms of our active systems, we decided to use a short duct air-to-air heat pump system, similar to the alley house if you're familiar with other Ball State projects. For our system, we want to create a good natural ventilation of air without overloading the system and putting too much air into each system, which is why we chose the active and passive systems we did.
And for the envelope of this home, we chose to use a structural system called the Larson Truss, which uses I-joists on the outside exterior sheathing of a normal stud frame wall for more blown-in insulation, such as cellulose, which is a low embodied carbon insulation and is recyclable as well. These joists can be removed if the owner or developer so desires to have a more affordable housing style, as well as, sorry about that. We also chose to go with the zip system as well to lower on labor costs as well. Going forward, we're still refining our design as well as sizing our passive and active systems as well. We believe that what we have now is a great base to start off with, and we thank you for your time. Thank you.
Thank you very much. You've timed it perfectly. Jurors, what would you like to know? Sue, if you're speaking, you're muted.
I had just a question. What's the foundation insulation and the roof insulation?
So far, we have a general idea of our ratings for our attic right now has about a 50R rating, and our foundation is around a pretty typical rating, though we still have yet to dive in really deep to specify exactly what system we're using, especially for the foundation.
And you mentioned earlier on in the presentation, did you mention modular and infill housing? So wanting to take on some of that, with the houses that are being taken down in the neighborhood. Can you talk a little bit more about the modular aspect?
Yeah, so what we kind of see this house as is more of a, maybe a design template or a solution to the infill areas. The Larson Trust, for example, that we touched on later on in the project, is just one of those examples to where you can modify this home to reach more affordabilities for certain developers or residents as well. Obviously, as you saw just on our site alone, we had almost 4 open sites. So hopefully this home can, you know, not necessarily be a defined solution, but something that can be adapted to other sites as well. So it could be just easier to infill and revitalize neighborhoods.
Great, thank you.
I love the architectural design and sharing the wall, and it seems, and the modular, do you have factories or anything already in your town that are making modular walls or designs?
We do have a wood shop close to our site that like we actually go there as a studio project to like work on some certain builds like furnitures or wood, like any kind of wood design. We do have a workshop for that.
For some of our smaller pieces, that can definitely work, but for some of our larger pieces, like the Larson Trust, we probably had to cite it from outside of Muncie, but definitely within the local Indiana area that we could definitely do that.
Great. That's a very valuable resource we're trying to develop in our own areas, more panelized systems and manufacturing.
You had mentioned the stack ventilation. I think, you know, going forward, those things need to be sized, and you had mentioned working on sizing them. Did you also mention active ventilation too?
Yes, that was our short duct inner air heat pump system. What that's supposed to be.
Okay, so would that be continuous? Wait, sorry, you said that was an ERV or an HRV or no?
I should have touched on that. It's supposed to work in tandem with our stack ventilation system. So we're going to have the short duct system work with in a passive and an active form, to where part of the time when our stack ventilation is effective during the day, that will work to ventilate the space. But when it's not, say in the winter, our ERV system would take over in a more active role.
Great, thanks. Yeah, that seems like a reasonable solution. And so just looking at the section of the home, the upper story, just your intakes and your outlets up high, you'll need to size those accordingly. And then that also changes during the seasons too.
I'm sorry, do you have your HERS rating before and after, and how much solar? Did I miss this?
Not in the presentation, no, but our current HERS rating is sitting around a 43 in our current design. But we're still working on optimizing our systems to hopefully get to a more desirable level.
Well, it looks like a great template for redevelopment. Hopefully your community will take this on.
Yeah, we hear you.
Great, thank you very much. We will now take a break. The next presentation will start promptly at. Sue, can you tip your screen down a little bit? We're just sort of seeing, yeah, there you go. And as soon as Sam joins us, we will begin the presentation.
Sounds good.
There we go. Jurors, are you ready? University of
Already.
University of Florida, please begin.
Hello, good afternoon. We are the Tabana Fireweeds representing the University of Florida. With industry partners, design partners, and the Tribal Council, we are developing a housing scheme to replace the many abandoned homes within the village of Tyonek, Alaska. Tyonek today faces a housing crisis. 40 miles from Anchorage, it's only accessible by plane or boat. Historic flooding necessitated relocation, destroying local building precedent. The Tabana, meaning the beach people, have led a subsistence lifestyle on the lands in and around Tyonek for thousands of years. We strive to respect their deep history and commit to careful stewardship of the land. Through collaboration with Tyonek's tribal elders, we have prioritized their unique cultural requirements, reliable energy, repairability, and durability. Our mission is to design and implement a high-performance, low-carbon house attainable for Tyonek's cold climate. The design honors Athabascan values of environmental justice and respect for their traditions and land. Existing vernacular precedent lies mainly in cultural and physical necessities, namely a wood-burning stove, a meat smokehouse, and a sweat, which is similar to a sauna. The existing electrical grid is inadequate and expensive, often leaving residents relying on their wood-burning stoves for space heating. We intend to replace Tyonek's abandoned homes first, and then turn our attention to assessing the condition of the occupied homes. Our goal is a prototype that will reinvigorate Tyonek's housing market, providing permanent housing for current residents and for those who have moved away. Tyonek has a median household income of $38,000, around half of Alaska's average. The predominant ethnicity in this location are those of Native Alaskan descent, with the typical age demographic being those of working age or older. Alaska's subarctic climate, particularly in the winter, presents unique challenges that have inspired our team to explore what's possible for the village. Whereas the summer brings warmer, longer days, the winter complicates PV electricity production. The sun rises only 5 degrees above the horizon for only a few hours a day. Our design surpasses simple code compliance, instead looking to Tyonek's future. The Fireweed is designed for Tyonek's multi-generational family with ample storage and a flexible plan that efficiently accommodates large events and daily life.
After discussion with the council, the desire for large, flexible communal spaces was considered a priority. In addition, we provided separation of public and private spaces in a 2-story plan. The home has 2 arctic entry points, one for public use and one for private use that contains storage and space for utilities. Living spaces, bedrooms, and other areas of prolonged stay or gathering are placed on the southern portion of the house, maximizing exposure to the limited winter sun. In the warmer months, blinds or shutters can diffuse unwanted light and minimize adverse heat gains. Conversely, storage and other transient spaces that don't require natural lighting are arranged on the northern edge. The aim of the design is to create a cool exterior to blend in with the surroundings and provide a natural wood interior to create a feeling of safety and warmth. The gabled roof profile accounts for the seasonal snowfall and directs snow shedding to desirable locations away from entry points. The continuous roof shape minimizes the building edges to protect against heat loss. The shape also allows for large open communal space and bedrooms and bathrooms to be stacked on the 2 floors. The envelope of the house is a thickened structural assembly constructed from wood trusses. The trusses create large cavities for insulation, resulting in a high R value envelope. They also create a large gap between any exterior surfaces and interior surfaces to prevent against thermal bridging. Truss construction allows for elements of the design to be prefabricated offsite and then shipped to the site via barge. The foundation system is tailored to address the potential for differential settlement and seismic conditions that can occur in the area. It consists of laminated beams supported by a series of jacks. These jacks rest on a footing assembly made from stacked 2x6s. The adjustable beam, jack, and spread footing system minimizes the effects of differential settlement and is robust to seismic events.
Integrating the PV panels vertically in the facade enhances their performance, considering the previously mentioned low sun angles throughout the year. The vertical insulation also maximizes energy generation and minimizes maintenance by reducing snow and ice accumulation. Furthermore, this placement allows for easy accessibility for a community that emphasizes aging in place. Interior and exterior wood finishes display respect for the natural environment. Life cycle assessments will be conducted and integrated in the next phases of the design process. Materials, products, equipment, and services will be sourced as locally as possible to minimize carbon emissions in transport. Using a metal roof and charring the wood siding will make the home more resilient to weathering in the cold climate, and at the end of the home's life cycle, these materials can be recycled or reused. Low maintenance and resilient materials are proposed to minimize the need for repair and to ensure that tribe members are capable of making any necessary repairs with relative ease. We are proposing a highly insulated thermal envelope to withstand the harsh Alaskan climate. As proposed, the house anticipates a HERS score of 34 without energy production. These assemblies follow the recommendation of the Cold Climate Housing Research Center, while also considering the assembly types and trades needed for installation. The envelope R values are still under review. They will be weighted relative to the skill and materials available and judged against the cost of the alternatives. Tribal elders have requested large open gathering spaces to accommodate tribal customs year-round. For example, residents may need ample space for processing game. Funeral rituals also take place in the home and require a simple direct path for moving a casket in and out of the house prior to burial. With this in mind, the house is divided into a large and adaptable communal space with bedrooms, bathrooms, service, and laundry making up the private spaces. Windows are located facing south to optimize sun exposure. Since the sun remains relatively low to the horizon, windows are relatively low to the ground to allow as much light to enter throughout the year. For our initial design exploration, we chose abandoned lot number 4. Here you can see the orientation to the south-facing sun, as well as the way the Arctic entry connects to the road. Assembly systems connect to minimize thermal bridging and effectively insulate the home. Given the expected contribution of electricity generated by the community solar farm, each individual home needs to produce an additional 3,350 kilowatt hours per year. Our 5 kilowatt DC system is expected to produce about 3,700 kilowatt hours per year when modeled in PV watts. This exceeds the requirements for Tionic. With these figures in mind, the system can expand, but it is a matter of cost for the individual. Given the challenges of construction in a remote site, we're proposing a balance between shipping prefabricated components and on-site construction. This balance will be adjusted as the relationship between material availability, transportation cost, skilled labor, and construction schedules are brought into better focus. The design we propose is ultimately for the people of Tionic and their environmental needs. We are excited to work with the community further to create a home better suited for daily life. Thank you for your time.
Thank you very much, University of Florida. Can you stop sharing your slides? And then we will have some questions from the jurors.
Great, nice presentation. I was just curious the connection between University of Florida and Tionic, Alaska. Could you talk about how you found each other and the start of that relationship?
Tionic actually reached out to us. They're looking for a better housing development system for their area. Currently, they have houses that were modeled after a mid-century California home. So they've been experiencing some issues just because they're not exactly adapted to their specific needs of their climate. So our professors went to Tionic and met with the elders of the tribe and got a better understanding of what they were actually needing for their daily lives. And we conduct weekly meetings with them throughout our process just to ensure that what we're proposing is something that they would be interested in and making sure that they're really involved in the communication of our design.
Great, thank you.
I just love the project. I mean, how you're integrating it into the community and using how the people live there and giving them a warm place to live. This is a really fabulous project and I hope it gets built. I have some questions on the solar panels being on the facade. Have you modeled what's the difference? We did this in the past. This is why I'm asking, is it just changing a townhouse from the north side to the south side changed our production by like 15%. Do you know how much solar you lose by putting it on the facade rather than on the roof?
I wouldn't say I have a specific number to show the difference, but the reason we were going more towards this vertical orientation was partially because of the ease of use for those who were living there. So with the intense snow conditions that they experience, having an angle would assume that it would collect snow. So the vertical orientation allows it so that they don't have to go onto their roofs and scrape it off every big storm that they experience. We have also considered a situation where we would have an adjustable angle. The only reason we haven't explored that further at the moment is just because it would be an additional cost as well as an additional maintenance in a system that is potentially breakable in a place that they do want to have kind of the age in living and that minimal effort. But it is certainly a conversation that we are still exploring with them. These figures that we've gathered are just simply facing the southern facade because that's where they experience most of their sunlight.
Good reason.
Thank you.
And you mentioned the $38,000 household income and your partnership, throughout this process with the Tionic residents. So affordability seems like a big issue. I guess, can you talk a little bit more about how you're addressing that? I know we saw a lot of the materials and the systems and things like that, but
as much as possible, the materials that will be used will be locally sourced, and the labor as well. It would be more geared towards things that can be prefabricated and built on site. And then as far as affordability, it is hard to say exactly how much the house would cost just because it's such an unusual situation and shipping is unusual. But in the long run, because the houses right now are so energy inefficient, it will end up being more affordable than the situation they have now. Their electricity, they're paying 3 or 4 times the cost of us here in the lower 48. So it'll end up being a positive.
There are also opportunities to receive federal grants and funding for this project that we can explore farther down the road.
And the way that land division works in Tionic is more in terms of the community. It's not exactly individuals buying a plot of land and building a house on it. It's more of the community owns the land, and then they gather the funding in order to provide for the homes. And then from there is when the individual would step in and pay for the home or rent it.
Great, thanks.
Can I ask about your hydrogen fuel cell and why that over a lithium ion? The technology, everyone's always high on hydrogen, but it's always 20 years out, no matter what decade you're in. And the maintenance and the breaking of fuel cells is notorious.
Yeah, with the hydrogen fuel cell, from our understanding through research, is that it exists more on the community scale. So in Tionic right now, they're looking into developing that community solar farm. So the plan with our solar panels is to connect to that grid so that we're part of like an integrated system of their electrical grid. In terms of the individual home, we're not anticipating to have a hydrogen cell system just because it doesn't seem as though it is, as you said, like reliable in the modern technology that we have. As well as I don't believe it's the most safe for a home individually to have such a technology such as that. So I think with the hydrogen cell, it's more of the community scale and building off of what they are proposing currently for their development, and then how we can also begin to integrate into it.
Thank you very much. That's all the time we have for.
Thank you so much.
Great project.
Great, thank you.
Great. Next up, we have the University of Massachusetts Lowell. Take a minute or two to prepare yourselves, and we can begin shortly.
Hello there. Sorry for the delay on our end. Just talking about the seating arrangement. How's everyone doing tonight? Today. It's not that late yet.
Wonderful. So we can see the two of you. No slides yet.
No slides yet. No, we're having one of our teammates pull those up now. You can go to presentation mode, Jacob, if you'd like. Is that visible to everyone?
There we go.
Thank you.
All right. The jurors are ready. You may begin.
We're just seeing some, I think your Zoom blocks are in front of your presentation. Just
Oh, yeah, bar there. Is there a way you can move that, Jacob? Maybe you can drag it somewhere else on the screen, or Oh,
they could, yeah, they could just go up to the top, maybe.
Would that work? Did that fix the problem?
That's better. There is another one on the upper right section as well.
This one as well.
Yeah, it's this guy here. I didn't know that Zoom did that. I've never seen that happen in Zoom before, so that's interesting.
All right, please begin.
Thank you.
Some call it the Venice of New England. Lol, there's a lot to like.
So the slogan of Lowell is "Art is the handmaid of human good," and we want to pay homage to that tradition through artistry and engineering. I'm Samantha Fiero.
I'm Alan Cook.
And we're here representing the Acre Artisans team of UMass Lowell, presenting to you a sustainable zero energy residence designed by our team of electrical and mechanical engineering students for the Solar Decathlon Design Challenge. So to introduce our city, Lowell is located in northern Massachusetts, located in climate zone 5. The humid climate here was a design concern, which we accounted for in the building envelope. Our design is new housing, a single family home, and it's intended to be built in the Acre neighborhood district, which is one of Lowell's oldest neighborhoods and has a diversity of cultures resulting from over 170 years of migration. Because of this, we want our Acre residents to be suitable for all types of families. Analysis of the current demand for housing in Lowell shows that approximately 1,100 single-family homes are needed to be built to account for the growing population needs. It was also found that Lowell homes have a 27% higher housing expense and 18% higher utility prices than the national average. So in order to meet the needs of the average Lowell residents, our prospect of sustainable housing also needs to be made inexpensively, and the lowered energy cost will hopefully incentivize the future residents monetarily along with environmentally.
Our goal is to achieve zero net energy consumption. To do this, we optimize our housing design using Building Attribute to Impact Algorithm, BIA for short. This software is a probabilistic whole building, whole lifetime life cycle assessment tool, which calculates building energy consumption, embodied in operational environmental impacts and costs. We lower the carbon footprint of the house by using low impact materials and having an airtight design, which helps mitigate loss. Lastly, the energy used in the house is offset by the energy gathered from an array of solar panels on the roof.
So the Acre Residence is a 4-bedroom home made in a colonial design, paying homage to Lowell's early American history. The 2,300 square foot area will be spread over an aspect ratio of 0.37, which is not reflected in the current floor plans, but was found to optimize the heating and cooling of the home. The top two images here are floor plans that were chosen from similar structures to represent the general layout of a residency, which we have credited in our slides. And the lower left-hand image is a representation of the house's exterior. The lower right-hand image is a 3D model created and used by our electrical engineering student team. So on the outside of the building envelope, you can see that we have some high R values to boast for insulating the home. Taking a look inside, we can see that the components that give these values. The windows are triple pane and argon filled. The wall exterior is insulation concrete forms, which help keep out the moisture and inclement weather of Massachusetts. These walls can be outfitted with R value increasing inserts, such as the Plus series from Nudra, and it also has a layer of expanded polystyrene foam beneath the ICF. And the interior frame of the wall is 2x6 studs filled with a fiberglass cavity for additional interior insulation. The roof has a polypropylene underlay beneath its cladding with extruded polystyrene foam rigid insulation and a final interior layer of open blow fiberglass insulation. Additionally, the exterior doors are hot dip galvanized steel with a wood interior, and the whole foundation slab of the house will be insulated with no basement.
Using an array of 25 415 watt panels, an annual energy output was determined to be about 13,600 kilowatt hours. The maximum energy production is seen within the month of July with an average of about 1,400 kilowatt hours. Comparing what the home consumes annually, the solar array produces an overflow of about 640 kilowatt hours per year. This overflow may be sold back to the grid for $179, assuming 1 kilowatt hour equals 28 cents, which is the mass average. These figures were found using the software PV Watts calculator. On the left is an energy use distribution of the house over a year. Over half of the energy use is through plug load, which highlights the efficiency of our airtight design and heating/cooling system.
So the HVAC system of this residence was selected using a cost-benefit analysis to decide upon the best market available system for our restraints. And that system was found to be the Mitsubishi mini-split system. Here you can see a representation of its necessary components. The total cost of the system, including labor, was estimated to be about $29,000, with an up to $10,000 IRA rebate and tax credit available to the end residents, depending on their income. Bioanalysis showed that 77% of heat that would have otherwise been wasted will be recovered and recirculated back into the home via the heat recovery ventilation system.
To reduce energy consumption further, an optimized layout of luminaires has been added to each room accordingly. This luminaire layout consists of only fluorescent and LED lights. The kitchen and bathroom have brighter lighting since they're most used rooms, while the bedrooms have low lighting since they are mainly used for sleeping anyways. The lighting simulations were made using a software called Dialax. Outlet installations throughout the home have been standardized to use B-type 15 amp, 20 amp, and 50 amp outlets. Most locations throughout the home, such as the living room, dining room, and bedrooms, have 15 amp outlets due to low current rated devices being used in these areas. Locations such as the kitchen and bathrooms have 20 amp outlets due to higher demand. And lastly, 50 amp plugs are reserved for high rated appliances such as washers and dryers. The PV system design is comprised of 25 panels that are mounted on the south side of the home. With a roof pitch of 0.578 and an aligned module angle of 30 degrees, an annual energy production of about 13,600 kilowatt hours is achieved. This PV system costs approximately $30,000, which would take roughly 18 and a half years to pay off. On the right shows the solar power production throughout the year, where more power is produced during the hot summer months. To promote a comfortable environment for the end user, the home is controlled using a brilliant smart home system. This system may control the lighting, heating, cooling, and security of the home. This system doubles as a means of increasing energy efficiency and improving the quality of life of the occupants. Additionally, the home includes numerous rooms that may be used for bedrooms, office spaces, and common areas in the hopes of providing a comfortable occupant experience. To reduce the energy consumption of the home, selected low energy consumption appliances from Samsung and LG were chosen.
So the estimated cost of the acre residence totals at about $258,000, including the cost of the solar panel array and the appliances. This was found to be 6.8% less expensive than the total cost of the local average home. The cost of the construction itself is estimated about $160,000, and over the course of the house's 50-year predicted lifespan, the homeowners will pay an average of about $19,000 in replacement material costs. BIA also helped us calculate the embodied impact of the housing construction, including the raw material extract, refinement, and transportation. This embodied impact was found to be 62.5 tons of carbon dioxide equivalent, which is 6.7% less harmful than the embodied impact of the construction of a similar zone's housing residence. On the right here, we have a visual representation of the carbon footprint of the acre residence in kilograms of carbon dioxide equivalent. And on the left, we have a comparison of our design's lifetime and yearly emissions versus a local average home. The emissions of our design yields roughly a 32% reduction in carbon emissions compared to the BIA calculated local average. Finally, the current design aspects of our residency may end here, but our ideas and future plans do not.
Next in our design process, we would like to continue work on our ideas of integrating a gray water system into the housing plumbing, work further on original floor plans with an architect advisor, Federic Kadir, and obtain a HERS score for our prospective home.
So thank you from our faculty advisors, team members, as well as the UMass Lowell community for your time today. We'd now like to answer any questions the judges might have for us.
Thank you.
Thank you very much. Yes, please stop sharing your slides and we'll go to the jurors.
We have our team filing in for Q&A time.
Sure, I have a kind of a kickoff question. So notice the floor plan is modeled after the colonial style floor plans in the area, and you mentioned that's it's staying in kind of character of the area. Were there any other considerations there for the floor plan, kind of mimicking some of the older homes in the area?
Mimicking older homes, the main concern there is we wanted to have our design fit in with the existing architecture in the Lowell area. And because this is a historical area, there are a lot of homes already built in that design. And while a lot of passive homes are made in a very modern sensibility, we wanted to have our home fit in, be comfortable, be recognizable as part of the Lowell community, because we wanted it to reflect the community.
Great, thank you.
Is that who the market is, though? Are young people buying there, or having a formal dining room is usually going by the wayside in new architecture.
This is true. Things like the formal dining hall and the breakfast room are not exactly things we'd like to have in the final floor plan, but more we needed to have some sort of representation in order to run several layers of analysis, including the luminary analysis. If any of the electrical engineers would like to speak about the modeling process they went through with that.
Essentially just laying out the luminaires in a way that was going to be most consistent with the actual floor plan. So trying to keep the dining room, living room, everything as consistent as possible is what we were trying to strive for.
We were unfortunately time restricted on the creation of an original floor plan time, and also skill restricted prior to this. And due to the fact that we wanted to have more representation available for the electrical side of our team to start doing the analysis that they wanted to do, we ended up using a temporary floor plan that didn't necessarily represent the allocation of space into rooms, but will represent the total area of the house ultimately.
You know, those floor plans, they tend to be fairly compact, and so some of the things that might be beneficial for your design is that compactness. So there's a core, typically a central core around these types of floor plans. But yeah, to Sue's point, it might be, I think it would be beneficial to kind of look at and reimagine some of those spaces that might be not as used in today's kind of daily life. Something to think about as a next step. And then I had a quick question about the carbon reduction strategies. I think that was a good analysis that you did. What were some of what was, let's say, one or two of the largest like carbon reduction strategies? You made a comparison between the acre residence and a typical residence. So could you talk a little bit more about that?
I guess that the main carbon reduction strategy there was focusing really on the building's envelope and ensuring we had as much insulation as possible. The main way that we did our comparison between our design process and the average home was we used SPIA, which we referenced a few times in there, as a Monte Carlo probability simulator, and the average home was kind of based off all possible types of buildings that BIA could create, reflected how they'd behave in zone 5 versus ours, which had specific choices that we had made through research to be found to be more energy efficient in some way or another, such as the aspect ratio that we chose was found to improve heating and cooling, the types of windows we chose, certain types of ventilation that we chose. And so in terms of the carbon emissions relating to the energy consumption of the house, that's that aspect.
Great, thank you.
Thank you. That's all the time we have.
Oh, that went by pretty fast, actually.
Good job,
Sorry,
guys.
guys, I talked a lot.
Nice work.
Yes. Next, we have the University of Arizona.
Thank you.
Hello.
Welcome. Yeah, get your presentation set up. Okay, we can see your presentation. The jurors are ready. Please begin.
Our team, Del Sol, presents Casa Del Sol, the prefabricated, energy-efficient future of living in Tucson, Arizona, that can combat the city's ongoing housing crisis. In the fight to create a carbon-reduced future, prefabrication is an asset, because if we can reduce the number of parts, make them lighter, and make the installation simpler, it will reduce the EUI and thus its carbon footprint.
Project is located in Tucson, which is the second largest city in the state. It is in the hot, dry, asteroid 2B climate zone and has monsoon seasons between June, and September, which makes it the desert as humid as Florida. Our project is located in Millville, a neighborhood south of the University of Arizona and downtown Tucson. It's surrounded by various historic neighborhoods and has a connection to major roadways.
The area surrounding the project has many vacant lots and is mostly zoned for single-family residential buildings. This means that there is a lot of space that is not being taken advantage of with a code that does not support density. With the recent allowance of an ADU in Tucson's building code, there is an opportunity for homeowners to offset mortgage costs by renting out their extra unit. We've spoken with the housing development manager at the city of Tucson, who has told us that an easily replicable design is very desirable for the many vacant lots owned by the city.
In Millville, a large portion of the residents are between the ages of 18 and 34, which means they are younger people looking for their first homes. Currently, the Tucson median household income is only around $48,000, while the national median is $70,000. With homes mostly being valued over $200,000, aspiring homeowners might find difficulty in keeping up the mortgage. An ADU is a great option as a source of passive income that can improve property values.
Casa del Sol is located on a corner lot, which greatly opens up the opportunity to have two entrances for the main house and ADU. Both houses have their own carport and small private courtyards to the north. The main plan has been oriented east to west in order to reduce western sun exposure and use passive design strategies. A large central courtyard connects the two residences into one cohesive scheme.
The ADU consists of one bedroom and one bath with a central living space that looks out to the courtyard. The main house is a 3-bedroom, 2-bathroom residence with an open main living area. Aligned doors on the east and west in both homes create a flow of ventilation. The public and private parts of the plans are separated for ease of construction and energy. The main house contains a mechanic room for both structures in an effort to conserve energy and resources.
The project emulates the vernacular style of residences in Tucson's historic neighborhoods. The most significant example of this is how the structures are stuccoed rectangular volumes with flat roofs, but some other nods that we've incorporated are the gated entrance, the masonry block walls, the carports, the wooden trellis covering the courtyard, and even the courtyard itself. But these design features aren't just cosmetic, they're common here because they're effective for mitigating the sun in this climate.
We're using advanced framing fabricated offsite, consisting of 2x6 studs, 24 inches on center. Thermal bridging is reduced due to the higher R value of the 2x6 and the reduction in stud area in the wall. Less framing also reduces cost. We partner with Habitat for Humanity Tucson. We fabricate these exterior wall panels offsite, but still in Tucson to reduce shipping costs and EUI. Here we've dashed in the 4x8 foot assembly. The assembly consists of zip sheathing, which provides a continuous air barrier to keep out water and air. Cellulose insulation is made from recycled newsprint and installed in walls via a dry pack process to reduce air leakage through the wall cavity.
Water is a huge resource in the desert, so it is imperative that we conserve what we can. In Tucson, there is an annual 11.3 inches of rain that has the potential to be collected. On the roofs of the two residences, approximately 16,000 gallons can be collected over the span of the year to follow a gutter system to collection tanks in the residents' private courtyards. A little over 7,000 gallons will be gathered off the courtyard shading structure to replenish the groundwater on site and aid landscaping.
Both units have their own dehumidifiers and heat pump water heaters, unlike the conventional water heater that is pictured. But the ERV and buffer tanks connecting to the radiant system are shared between the units. During the day, all of this equipment can be powered by the solar array, but to reduce grid reliance at night, the system also pre-chills additional water. This is why there are two buffer tanks, one to hold water at 60 degrees and the other to hold it at 45 degrees. This second tank essentially stores renewable solar energy that can be utilized by the mechanical system at night. And this strategy is significantly less expensive and less dangerous than chemical residential batteries, which can be a severe fire risk.
The central courtyard between the main house and ADU allows for visual and physical connection between the residents, whether the ADU is being used by an elderly relative or rented by a college student. The shaded courtyard creates a community space to enjoy this extreme climate of Tucson.
A primary way of maintaining occupant comfort in Tucson's long cooling seasons is to remove heat from the people, objects, and the services in the space using radiant cooling. With our super efficient belting envelope, all we need is 60-degree water circulated in radiant tubes embedded in the entire ceiling to maintain comfort. Radiant systems are used because it is more efficient to move chilled water around the space instead of moving air. Since only minimal heating is needed, only about 10% of the floor and the perimeter has radiant tubing in it to maintain occupant comfort. We're investigating whether it's better to insulate under the slab or around the perimeter, considering comfort, cost, and embodied carbon.
As we mentioned before, Tucson does have humid months during the summer. So even though the radiant system is much more energy efficient than forced air, it comes with the additional requirement of dehumidifiers. Without them, there would be condensation whenever the dew point is at a higher temperature than the 60-degree radiant tubing and would likely cause mold to form. And to improve the efficiency and speed of cooling, we've opted for a recycled corrugated metal ceiling that will easily conduct heat to the warm-board piping system. The added benefit of this material is that its ridges will reduce echoing in the interior spaces and enhance comfort inside of the house.
Project utilizes FIA's prescriptive and its passive house principles, including proper solar orientation, climate-specific insulation, high-performance windows, and an airtight enclosure. With Tucson having more cooling degree days than heating degree days, the annual cooling demand in both structures is elevated. The cooling load between the two buildings is between 5.2 and 10 kilobTUs a square foot per year.
As we move forward past the semifinal, Del Sol looks to achieve our design goals with more detailed ventilation, plumbing, lighting, and drainage strategies. We'll be modeling Casa del Sol in new Woofy Energy software to optimize the building to FIA's core standards, and we will also be finalizing the cost for the project's construction using RS Means software. And as we develop a higher level of detail in the design, we are very focused on making the wall panels and other components as replicable as possible.
Finally, we would like to acknowledge our design partners, Water Buying Engineering, and our various other partners. Thank you for your time.
Thank you very much. Jurors, please add something.
Bravo.
Thank you.
Go ahead, Sam.
Yeah, sure. I just wanted to let you know that picked up on something that was really critical with your radiant cooling design, which is the dehumidification. You just mentioned that you do have some humid summer days, and that is going to be a critical part of that radiant cooling and heating system. So very nice to hear that and include that in the system thinking. That's sometimes not picked up, so way to go. And I think just why, could you talk a little bit more about just hydronics and why you picked that system? I know you put that in both the ADU and the main house, and it's the first system that we've seen today. So can you talk a little bit more about that?
I can take that. So a rated system, it requires less space and less energy than a forced air system. So the ceiling, wall, and floor temperatures are really important to our occupant comfort. You know, if the walls are hot and surfaces are hot, you know, you're not gonna be very comfortable in that space. So blowing air also can be a lot louder than the radiant systems. So really, we're truly trying to increase occupant comfort and kind of decrease the energy we're using in that space.
Great, thank you.
What size is your solar panel? You have 2.6 kilowatts per day?
Yeah, that was a mistake on my part, actually. So we have 20 solar panels and each of them are doing a 2.6 kilowatts per day. So I did the math a little wrong there. Sorry about that.
No, but what's the kilowatts? Like, is it a 5 kilowatt system or a 10 kilowatt? Not the electricity load, but the capacity.
We have not selected the exact system yet. That's something that we're looking into for the final submission.
Oh, okay. So do you have a HERS rating before or after? Or any estimate?
So again, since we're using FIA's prescriptive, we've been focusing on that and we have not yet calculated our HERS score. But in this region, FIA's homes are ranging around 30 to 35, but we believe we can get that number even lower using the solar and these various systems FIA's requires.
Great job taking the next step into FIAS. It's wonderful.
Yeah, that was great to see. I just have one quick other question. So you're prefabricating these panels and using, I know stucco is a local material, but those two processes of prefabrication and on-site stuccoing, they're a little disjointed. Can you talk a little bit more about the choice there? for prefabrication and stucco?
Yeah, well, we felt that the stucco is a very common design element, and it's one of the potentially the most common elements that we see in the houses around here. And so we felt that that was an important and relatively inexpensive feature to include, even though it can't be applied until after the panels are assembled. We felt that it would reduce the cost of having any other form of cladding and still keep it in line with many of the other houses nearby.
Great, thank you.
So is it going to get built?
I hope so.
We are hoping so. That's because we have been speaking with the housing development manager at the city of Tucson. We're hoping that eventually this could be built, or this could be used as a guide for some type of physical project.
Great. Good luck with that.
Thank you.
Fantastic. Any other questions from the jurors?
Can I buy one?
Yes, we do have another minute for you.
No, I want to buy one of their houses.
Ah.
I think we could work with that.
I guess since we do have another minute, yeah, can you talk about the in-between space and how that was designed between the ADU and the house? I think it's a really great asset to the project.
Yeah, the courtyard is another common design element that we see in the houses nearby. So that was another thing that we really wanted to include. We also felt that since there was the ADU separated from the main house, we felt that it would be beneficial to have a space connecting the two, that we could include some landscaping and have a nice outdoor space that can be shared by both of the units. And it also fits very well into our water harvesting goals, so that we can divert a lot of water into the landscaping between the two units.
I believe also in a way it might have some kind of cooling effect with the water collection there, and being able to open those doors to that courtyard with the breezes coming through from the southeast and southwest. It might have a way of cooling that space as well.
Thank you very much. That's all we have time for now.
Thank you for your
Thank you.
Thank you.
Thank you.
Thank you.
Great. Next, the University of Waterloo. Take a moment to prepare your presentation. We're still seeing your entire PowerPoint window, not just the present view.
Yeah, it's just taking a minute, unfortunately, to open up the presentation view. Sorry, just one moment.
Is it working, Anna?
No, I'm sorry. My PowerPoint just crashed. Are any of the other presenters able to share the slides quickly?
Renee, are you able to?
I can open them. I don't have them open currently.
Yep, thanks for your patience.
Yeah, sorry about that.
A 3-woman design team. This is kind of nice. Yeah, very often.
Speaking of which, we do have a 4th presenter. Is he here?
If the 4th presenter doesn't show up, we
Oh,
can
okay. No, he's in
continue.
call. He's in
Okay,
call.
that's good.
Phew.
Oh my gosh, technical difficulties.
Yeah, we're gonna start your timer just to be fair to all the other students.
Yes.
No worries.
I don't know what's going on with PowerPoint.
Caitlin, do you have their PowerPoint? Can you run it for them?
No, we don't, unfortunately.
There you go.
Oh, we see that.
We see something.
Amazing. Okay, I'll present.
Just go with that. We don't need it in presentation mode.
Okay. Hi. Oops, I think I'll need my script though. Judd, are you able to present?
Oh my God. Where is Ashton?
No.
He's here, but this is fine. Just let's begin.
Yep, let's begin.
Okay. I just need to share another screen. Okay. And then
I love when my computer crashes. That's all I'm going to say. Sorry for this. Anyways, let's start.
You also see my script?
It's all good. Let's go.
No, you're good.
Okay. All right. Welcome, judges. We're Warrior Home, a fully student-led team based at the University of Waterloo. My name is Adriana, and I'm here with Anna, Judd, and Renee. We are a team of 21 students here at the University of Waterloo, and this year we're making a project on 57 Broadview Avenue at Kitchener, Ontario.
So for this design challenge, Warrior Home has partnered with the Kitchener-Waterloo Urban Native Women Project, who are an Indigenous nonprofit organization in Canada. This Indigenous housing nonprofit has many properties in Waterloo, which are old and in such bad condition that retrofitting doesn't really suit the client's needs. See, the organizer was pretty pleased to hear that the selected site we were having was going to be a new design because the current home there had many land issues. So Warrior Home saw potential to help our partner making energy efficient, sustainable, and affordable homes on their existing properties. And hence, this first design proposal has the mission to seamlessly integrate net zero homes within the neighborhoods without compromising comfort, reliability, and quality of traditionally built affordable homes. So all the properties our partner has are to be demolished, and it seemed right to choose a design partner who could fabricate the home while demolition works was happening and had industry experience within passive house design. Hence, we've been working with Quantum Passive House to come up with the design shown today. The building is situated on a narrow lot in a suburban area of Kitchener with easy access to transit and relatively higher walkability. Nearby is downtown Kitchener and alongside a church and park. Homes are modest and exemplify the vernacular style of the region. Much of the development is single detached homes with the population age group in the working force. Our home is the teal on the bottom right for reference. And as a result, our building aims to introduce high performance building standards without interrupting the existing community fabric.
Our site is located in a temperate climate zone with warm summers and receives precipitation year round. Freezing occurs during the cold months, and the heating needs greatly exceed the cooling needs over the course of a year. Next slide. Solar energy availability varies significantly compared to in Golden, with our peak solar hours ranging from 6 hours per day in July down to 2 in December.
Similar to many of its neighbors, the two-story home greets the street with a porch and is clad in standard wood siding exterior. The open gable roof also provides plenty of space for solar panels and while adding the simplicity of construction. The 4-bedroom home has natural sunlight and opera windows and also forms a subtle buffer between the foyer and family spaces, retaining a smooth flow of traffic from exterior to interior while facilitating a shift in volume and function by introducing corridors and walls. Additionally, the first floor bedroom is larger and designed without a built-in closet, making it more suitable for spaces like an office and additional family room. Inside, the layout centers around the many gathering spaces for the family, a double height living and dining room, a cozy nook on the second floor that looks above the living and dining, and a sunroom that leads into the large tree-lined backyard.
For the enclosure, we are using Quantum Passive House's prefabricated wall panels. They are Passive House certified for the cold climate and have an R value of about 64. The assembly consists of a double stud structure with 16 inches of EcoBat insulation enclosed with Menta water barrier and IntelliX vapor variable air barrier. There is also a 2x4 insulated service cavity for MEP.
The amazing thing about these panels is that they can be installed on site in just 1 to 2 days. The roof will be built with prefabricated wooden roof trusses, and the attic space will be filled with 24 inches of blown-in cellulose insulation. For the walls, the panels will be stacked on top of each other with the second floor joist hanging from the first floor wall panels. We will be supporting these panels on a raft slab foundation system. The concrete will be poured into an EPS boat with 16 inches underneath and a 10-inch curve. The windows will be Passive House certified. They will be triple pane, argon filled with a low E coating, and thermally broken frames. The two main aspects of our design contributing to the environmental impact are the materials and the use of prefab. Cellulose is being used as it has one of the lowest carbon footprints for insulation types. EcoBat, as you saw, is the wall panel insulation, and it is made out of mostly recycled materials. EPS and timber have better environmental impacts than other options, and using prefab means that there is just less waste in construction. The floor plan tries to lift the user experience by bringing the outdoors in, especially with the use of the sunroom. The open to below area allows lots of sunlight into the communal spaces, and the addition of a bed and full bathroom on the main floor mean that elderly residents are more than welcome. By using the Passive House standard as a design basis, the interior climate of this house will be completely independent of the exterior temperature swings. Our mechanical system is a split heat pump with an outdoor condenser and an indoor air handling unit for heating and cooling. We will also be using an energy recovery ventilator for the ventilation system. These will be integrated into the same duct system by connecting the fresh air supply of the ERV to the intake of the AHU.
Our proposed solar power installation has a nameplate capacity of 9.45 kilowatts, estimated to generate nearly 10,000 kilowatt hours per year when considering significant losses from snow. Our system does not include any energy storage. We instead plan to connect to the grid using a net meter, which allows us to draw power when we underproduce and to receive credit for power provided to the grid when we overproduce. This significantly reduces capital cost while still allowing us to achieve a net zero energy annually. We've selected a string inverter so that the system is islanding capable in the future. Solar energy generation is a crucial system contributing to the integrated efficient performance of the home. The pitched roof maximizes the solar incidence and overhangs to shelter windows from the summer sun. Passive House certified windows further minimize unwanted solar gains and losses throughout the year. We evaluated our energy performance of the home using Ecotrope. The home itself is estimated to have a HERS index of 30, which is 70% more efficient than a standard new home. With energy generation, our home is projected to perform better than a zero energy home with a HERS index of -2.
This phase of our project estimation was mainly conducted with RS means, with overhead and profits, labor costs, and a 20% contingency cost applied throughout. Our final estimate resulted in just above $200,000, and our final cost per square foot is around $133, which aligns with average square footage prices in the Kitchener region. Following the semifinal stage of the competition, our team will focus on finalizing more components and small quality assurances to be able to have it signed off by not only our partners, but also structural engineers by April. With that, our cost estimate will be refined from Class D to B once we have vendor pricing, and we will produce details such as multimedia pitches throughout the next month.
Our
Thank
mission
you
is
very much. That's all the time we have, unfortunately.
Yep, all good.
Well, we were done anyway, so that
Yeah.
works out.
Thank you.
Jurors, yes, please begin.
How many square feet is this? I'm sorry.
I know it in square meters. It's about 150 square meters. So I think that's about 2,000 square feet.
Yeah.
Something like that.
Times 9 is about 450. Okay. 1,500. So that's a lot of solar for 1,500 square feet. But you're in a pretty cold area, I understand.
Yeah, that's right. It's more challenging to meet our needs given that in the winter we're producing so little, which is why we choose the net metering approach.
But you're Passive House, so you shouldn't need any kind of HVAC, right? Or any.
Very little, right? Yeah. Yeah, do you have a cooling load in the summer?
Yeah, yes, there should be. Did have our load calculations in the slides somewhere. But yes, in the summer there will be cooling. So there will be like some cooling needed, but hopefully with the use of very good windows, that will be mitigated.
Sure. And what would I know your square footage cost was 133 per square foot. Do you know what the average cost is in the area?
Yeah, so the average cost starts around like 115 and it goes upwards to like 250. And then beyond that, 400 plus is for, bespoke homes. Again, this is a Class D budget. We do expect the budgets to go a little bit more higher, the 200 to around 300, but that seems very feasible for, again, a net zero home here in Waterloo.
What's your land cost?
So the land was acquired from our nonprofit organization for $1 because they got it out from the government. It was not in use for a long time. Then they had to tender it out. Many nonprofits applied and they got it for, again, $1. So we've acquired a land like that. And our nonprofit has multiple lands like this where they have existing homes that they acquired for $1. You can see they were not used for a long time, so they're in very bad condition.
I have a question on your naming of this project, the Warrior House. We have a lot of controversy in the United States on as far as American Indian naming. Is that derogatory in any way, or
No?
Warrior Homes, that is exclusive to the university. We're the Waterloo Warriors. That's the team name. The Kitchener-Waterloo Urban Native Wigwam Project is the nonprofit's name. They're completely detached from one another.
Yeah.
Yeah, Warriors are our school mascot.
Yes.
And there's no controversy there at your school?
No, we've been working with actually our current project partner for our build challenge as well. So we've had a really great relationship in terms of that.
Well, great. Thank you very much.
Great project.
Yeah.
Thank
Wonderful.
you.
Thanks for your patience.
Thank you for your
Now, before our break, we have the Pennsylvania College of Technology, and then we'll take a 10-minute break.
Hello.
Good afternoon. We see the presenters. No slides yet.
Yeah, I'm trying.
Maybe Ms. Karen is better at this.
Where is it? Yeah, do you have the, do you know where the screen share button is?
It should be down at the bottom, where it says share screen and the green.
Oh, right there. All right, can you see that now?
Yes, we can.
Okay. Okay. So, hello, I'm Carter Simcox.
I'm Sadie Niedermeyer.
I'm Steven Adams. I'm Mark Dosa. And I'm Michael Drake.
And we have a number of students that can't make it today, but we do have many more people on the team. And we're here to present our proposed project for the new housing competition. Here you can see an interior rendering of our home and some of the basics of our presentation. So for our project, we are partnering with the Greater Lycoming Habitat for Humanity. We were asked to design a 3-bedroom, 1 to 2 bathroom, about 1,200 square foot home
And we've met with them a couple times now, and we've met with the director and the project manager or building manager. And we've gone over some of the stuff, and we're working to meet their national standards. And our goal is to meet about $200,000. We're also partnering with the Pennsylvania College of Technology. Penn College students will actually be building this home in the future, and Penn College is donating our site for our project, which is located at 508 Fifth Avenue in Williamsport. It's about 1.6 acres, and it's just a few blocks from our campus, which has allowed us to go and investigate the site and actually take a look at some of the site conditions. We were able to, check out what the site looks like, some of the surrounding homes, and it's right around a lot of the things in Williamsport. It's within walking distance of our campus, downtown Williamsport, and even the hospital. So some history on Williamsport. It was established in 1806 and quickly boomed and became the lumber capital of the world in the 19th century. During this lumber boom, it housed the most millionaires per capita in the world, which, we have a Millionaires Row now, and the high school is called Millionaires. So there's a lot of history in the city. It's also home of Little League Baseball, where thousands of people will come to Williamsport and enjoy Little League World Series. Now onto our building. For the structure, we're using 8-inch ICFs for the basement, and we also have steel column posts to support the floor system. For the walls, we're using basic stick framing with a double stud wall on the exterior, 6-inch for the interior stud, and 2x4 for the exterior. We are using 2x12s for the rafters, and we have 1 3/4 by 14-inch LVLs for the roof structure. We're also including some columns to help support that roof. In the floor plans, you can see that we have 2 bedrooms with a master bed, and it has its own master bath and walk-in closet. We've also included the kitchen, dining room, and living room, which we've called the living space. We have a full laundry room, full bathroom, and then a mechanical space that allows us lots of extra room for our mechanicals. And then we can have our runs in the attic space or in the crawl space. We've also located that mechanical space up in the corner where a lot of our hookups are on the site. The plumbing plan shows where our runs are going to go. Very simple, very easy to install, very cost effective. Straight runs that will allow us to use whatever sort of materials we want. Like I said, we will be able to run those in the crawl space or in the attic space. Our elevations begin to show the basic form of our building. Some of the materials that we'd like to use, some of the natural materials, stone and wood. We also are planning on using asphalt shingles. We're not 100% sure what we want to use for the siding yet, but we're looking to use something natural, something low carbon, and because we're trying to reduce our carbon footprint as much as we can with this building. In our building section, you can see the basic makeup of our building. The roof system, the wall system, the floor system, the foundations, and then the building envelope, if you'd like to talk about that.
So I'm just gonna show you with the cursor right here, if you can see it. Our thermal envelope is going, so this is the vaulted ceiling in the living room. So it'll be right up against the ceiling, all the way down and into the crawl space as well, will be the thermal envelope. So there will be the air barrier in between the double stud wall, and then the drainage plane will be on the outside face of the wall. So that's just in terms of for the passive house where we'll be putting those barriers.
And we will be using blown-in cellulose for the walls with an extruded polystyrene foam on the outside, and then cellulose in the roof as well.
Another thing to mention about this vaulted ceiling though, adding that volume also helps with the efficiency of the ERV. So that was another reason why we chose to do the vaulted ceiling in the living space.
These are some basic renderings of our home, just showing the makeup of the home, how it's going to look in 3D, and some of the materials. Again, you can see our aim was to have a very simple, very functional design, but also be attractive and sustainable. For energy analysis, we have listed some of the systems, some of the insulators and materials that we've used. These have all contributed to getting our EUI to 34.2 without our PV system. With the PV, we get it down to 1.6, and we're also aiming to achieve a passive house certification on our home. We're working with Habitat to reach that. And with the PV, our HERS index is at -2.
So then another few things that we're doing to meet the FIAS standards is, as I mentioned, we're going to have the energy recovery ventilation system, the ERV. So that will either be placed within, since the attic space and the crawl space will both be within the thermal envelope, we can place it in either one of those depending on how we end out working everything out. And then, as I mentioned before, the placements of the barriers, and so the double stud wall is contributing to that, meeting the high insulation requirements for the passive house. Our roof is even, the long portion is facing the south, so I can go back to these split plans if you want to talk about that. So this is east to west right here, where most of the living spaces are facing the south. It'll be beneficial then to put the solar panels on that face, and we're optimizing the use of the solar exposure for the yard as well as the through the solar gain of the windows.
Yeah. No. But yeah, that's all we have for you, and we're really eager to hear your feedback. So thank you very much.
Thank you very much. Yes, let's hear from the jurors. What questions do you have?
Yeah, I have a question about you're talking about your duct runs and where you want to place them, which is preferable. So you have a vaulted space, right? Is it just in the living?
Yes, it's just in this living
Just in living. Okay, I see. And just through your analysis, I know everything's within the thermal envelope, but do you have a preference, crawl space or the attic space in your climate?
I know for us, I think we would rather probably do it in the crawl space, just because you're losing most of your heat out of the attic space, and our climate is primarily heating dominated. So we'd like to keep most of that heat in if we can. Also, I personally would think it would be easier to run most of that stuff in the crawl space, but.
Yeah, and how big is your crawl space?
I believe it's about 4 feet.
Oh, okay, that's significant. That's
Oh no, I'm sorry, it's a little less than that. We're at about 3'10" to the top of that foundation, so we're sitting at about 3 feet.
okay. Yeah, just thinking about access and a clean crawl space, that's something that is certainly doable, but just thinking about access and maintenance for those systems.
I'm sorry, what is the heating system? A heat pump or?
Right now, we're looking at using a mini split system. We're not 100% sure what system exactly we'd like to use, but that's about what we're thinking right now.
That might also be something that we have to verify with the Habitat for Humanity, like if they have any guidelines for what they need to use to meet their requirements.
But didn't you need that to get your HERS rating?
Yeah, right now we have the mini split system on for our energy modeling.
Oh, okay.
And that works with it's an 8 kilowatt array. Is that correct?
That's great that you get to see the project right there in your backyard and use it as a school experiment. This is super fun.
Yeah, it's really cool that we're designing it as students, and then we also have construction masonry students that will be able to actually build the project in the next couple of years.
Nice.
There are also future projects that may potentially happen that will continue to maybe even create almost like a class for the Penn College, that future students will keep working on these habitat homes.
Yeah, I know right now we're only working on one of Habitat's homes. They're projected, I believe they want to build 10 homes with a budget of about $200,000 each. So hopefully we'll be able to get involved in some of those, but this is the first of those 10.
My only comment is on the floor plan, having all the plumbing all across instead of having it like compact in the center. I know it's a pretty small 1,200 square foot house, so that's pretty small, but would it be better to have your mechanical room towards the center instead of all the way out by itself?
The electrical hookup and the water hookup are actually on that right up here on this portion of the site. That's why we placed it there, because it would be a shorter run for the energy, the ERV hookup and whatnot. And most of the plumbing is still right here, pretty close to the mechanical. But even then, yeah, maybe flipping it might be beneficial.
Yeah, that's something that we'll just have to look into, but
yeah,
that is the reason why we put that there for now, at least.
And then you said it's cellulose insulation in the roof, and your roof plane is your thermal envelope. Is that correct? And it's a 2x12 rafter.
Yes, that's correct.
Yeah, just in your climate, I would double check to make sure that's enough insulation up there.
Okay.
You might need to go to an LVL or an I-joist.
Well, thank you very much. Let's take a break for a few minutes in case anybody needs a bathroom, and we will come back for 2 more presentations for the end of today.
Yeah,
Thank you
nice
very much.
Thank you.
Thank you.
Great work.
Hello? There you go. Hello?
Hello? I'm so quiet. Can we bring it out?
We could sit closer.
Can we just move?
I think it's a 10.
If I'm talking into it, well, like it is detecting.
It's not. Is it detecting me?
Oh, it's still. Oh no, that's just the feedback or something. I think if you just want to close into it.
Okay.
Yeah, right.
Let's pick him down.
Yeah.
Yeah,
okay.
sit here now.
Slides.
Welcome back, jurors. University of Canterbury, are you ready? Augusta, you're muted.
We have a speaker in our room.
There, now we hear you.
Awesome.
But yeah, we do not have any slides yet.
Working on that.
Great, we can see your presentation.
Wonderful.
Yeah. University of Canterbury, whenever you're ready.
Hello, we are the University of Canterbury from New Zealand, and this is the Kainga project. Kainga being a Māori word, the indigenous language of New Zealand, that means home, dwelling, or settlement. We had a group of entirely engineering students. Got Bill as our faculty lead, and Finn as our student lead. We also have Gussie, Nadia, myself Campbell, Chris, and Brian. We are also joined by a group of local organisational and industry partners. A little bit of background on New Zealand. We've just surpassed a population of 5 million, and we're still growing rapidly. We're all living on a landmass similar in size to that of the UK, Colorado. We're located in the South Pacific, just below Australia, and have a temperate but extremely variable climate. Our build is set in a suburban coastal area. Of note is that New Zealand is located directly on a fault line, resulting in significant earthquake activity. A primary motivator for us is the rapidly rising cost of living and population in New Zealand. This has resulted in much of the younger generation struggling to buy single-family homes for themselves. Instead, they are turning to multi-generational homes. This is backed up by data showing that the amount of people living in multi-generational homes is increasing faster than those in single-generational homes. Our design aims to meet this new need for multi-generational homes, while also tying in with our government's aim to increase urban density and functionally affordable housing. We also aim to support local businesses and innovators who are making advancements in the sustainable building industry to meet our 2030 and 2050 national emissions targets. With this overall goal in mind, we've developed a detailed project outline. We're currently finalizing our architectural and structural design, which we'll hear about soon, and are moving on to building modeling. From there, we'll focus on developing specific engineering systems and experimental trials where we aim to create our own hempcrete and test it in real-world situations. With these systems and data, we'll have the final puzzle pieces we need to complete our overall design.
As Campbell touched on, New Zealand is currently undergoing a pretty severe housing crisis. Our housing stock is unaffordable, but also very low quality. That's why this project aims to draw upon intergenerational wealth accumulation so that we can provide the capital for a high quality build. NZ is also a diverse society under several cultures who value intergenerational living. While our target market here isn't for a specific cultural group, we have accounted for some common cultural taboos in our design, and these provide a really useful framework for people who have successfully lived in this way for a long time. New Zealand building codes have historically been far behind international standards, which has led to our systemic problem of unhealthy and inefficient homes. In recent times, these codes have been repeatedly revised, but this has led to a very convoluted and confusing regulatory environment. And you can see from these R values here that our 2022 current code is still below international standards, and a house built to the current New Zealand standard isn't going to be good enough to get us to our emission reduction targets. And so we've designed the building with significantly better R values. Essentially, this project, we're trying to set a precedent for a viable out-of-the-box design to get us closer to these goals. So the first step of the architectural planning process was figuring out the functionality required from all the different spaces and how they needed to interact with one another in a way to make multi-generational living actually viable for people. We then looked at more literal space constraints and engineering constraints like plumbing and utilities and orientating the house on the side with sun angles and things. We then talked to an actual architect who gave us tips about things like using modular blocks for ease of construction, where to locate structural members, and ways to hide transitions between spaces to create a sense of openness. So here's the current state of our design concept. It's a multifunctional super home. And essentially, we want this to be a high quality build that will last a long time and conserve the user's needs throughout different life stages. And so we try to do intelligent design from the very beginning so that we can make that happen.
The majority of Christchurch is built on severely compromised land, which creates a big hurdle for constructing new housing due to foundation requirements and liquefaction risk. This has led us to the locally produced solution of timber raft foundations, which are cheap, readily re-leveled post-earthquake, good for shallow ground conditions, and low in embodied carbon, being comprised of timber and soil. While a great solution, this raft foundation stipulates that the building itself has to follow lightweight construction protocols. This leads us to timber framing with interspersed use of hempcrete and Terralana wall insulation at 1.7 and 2.8 R value per inch respectively. The biggest factor in choosing these materials are the low embodied carbon properties and being local solutions. In fact, over a life cycle, hempcrete will sequester carbon whilst offering great humidity buffering and acoustic regulation. Historically, hempcrete has been widely adopted globally in vastly different geographies and climates, and furthermore has been certified through New Zealand regulatory channels. Provided it is accounted for in the detailed architectural design stage, installing hempcrete will be a linear process and presents a great opportunity to showcase its usage as what could be a standard building material. Next slide. Water is becoming more valuable as the years go by and population demands increase by the projected intensification of Christchurch City. It needs to be carefully moderated in order to ensure ecosystem stability and sustainability of the water table for future uses. With 3/4 of the city's water supply coming from the river northwest, it is important to address this early. Housing 10 occupants, we expect these issues can be addressed through clever engineering systems involving water reuse, rain collection, treatment systems, bringing water consumption down by 48% compared to the average New Zealand household, which is in line with what the council believes.
To evaluate the energy performance of our design, we used a local green building rating scheme called Homestar, where a score of 5 represents a standard reference home, and a score of 10 would be indicative of a world leading build. So our current Homestar score of 7 puts us with an indicative HERS rating of approximately 42. However, we would be intending to further develop the design to achieve a Homestar rating of 8, which would put us in the region of a HERS rating of approximately 30 before the addition of renewables. However, we can anticipate that we would further reduce this HERS rating with the installation of a 9 kilowatt fixed angle roof mounted system, where the north facing orientation would maximize the solar gain potential of this system for the entire building, allowing us to account for the cumulative operational loads of all our occupants. We are quite lucky in New Zealand being able to use a highly renewable grid to help balance some of the deficits you see in these load profiles. However, we would also be implementing further load management schemes to further optimize these shifts. Our next stage of the project will involve conducting an experimental trials on some of the proprietary materials and construction techniques, taking us through to an in-depth evaluation of our design using tools like LCA and financial forecasting, along with more in-depth energy modeling software such as Woofy or OpenStudio. This would then stage the way for us to produce our final project deliverables. So in summary, New Zealand has a history of very poor housing, often not catering to the needs of our diverse society. And so multi-generational living provides a unique alternative way of improving this urban density, whilst actually providing a more suitable environment for many of our extended families that we have in the country. So thank you very much for listening to our presentation. We'd like to take this moment to thank all our supporters that we've had throughout the project and welcome any questions. Cheers.
Thank you very much. It's great to see some people from the Southern Hemisphere. Jurors, please ask away.
Yeah, I'd like to ask you a little bit more about the multi-generational living and kind of the, the plan is derived from that scheme, and just wondering about if you could talk a little bit more about kind of that trend or just that cultural desire, I guess, in Christchurch right now.
Absolutely. So I'll just clarify, you're kind of wanting to know a bit more background around the cultural incentive of our target demographic for multi-generational living?
Yeah, just the multi-generational living. And is that particular to the Maori, or is that just more generally?
Also, briefly, before you start, Finn, can you guys stop sharing your slides and show your faces larger? Thank you.
Yeah. All good. So the multi-generational living is a style of living that resonates with some of these cultural minorities in the way that they prefer to have the support of larger families. However, what we're seeing currently due to the housing crisis in New Zealand is that it is becoming an adapted way of living for the wider population as well. And what we actually showed in that initial the figures was that more and more people, in fact, more people by number are living in extended family dwellings rather than single family housing. So as much as we would like to cater for some of the minorities that have maybe been overlooked in the historic housing market in New Zealand, we are designing for the wider population as well.
Great, thank you. Sue, you're on mute.
Thanks. Can I ask about the costs? 1.2 million, is that like an average house in Christchurch? I've been there before, but I never shopped for houses.
Yeah, I'll pass that on to Campbell.
So what's the question again? So it's what is the average cost of a house in Christchurch?
Yeah.
Yeah, around 1 million. We for a while, or if you heard of Auckland, that was our largest city in New Zealand, and for a long while the average cost of a house there was 1 million, and Christchurch was kind of the affordable place. But as Auckland is becoming more and more overpopulated, people are starting to move to the smaller cities, and so our housing costs are rising very quickly to meet that demand. So around 1 million or even slightly above that would be pretty typical for a house
of this scale, for sure.
I was gonna say, do people build like 1,200 square foot houses, or everybody just lives in huge houses? Or why such a large house, I guess?
This design would be considered unconventional. However, it's an alternative to more typical social housing where they are usually made up of lots of smaller units, where we're catering for a similar number of occupants for a overall building that size, but having more collective spaces and integration between the different types of occupants within a multi-generational family.
So who would be the buyer of the house, I guess?
The buyer would be a community supported fund, I suppose, that is supplied from all parties within the family. So a parental group would gather support from maybe grandparents or other extended members of family.
Okay.
I wanted to ask a little bit more about the Timber Raft Foundation. And so through your research, is a typical foundation type? Is that kind of looking back into what has worked in the past, or is that currently being utilized on a number of projects in Christchurch?
Please answer briefly. We're almost out of time.
Okay, I'll keep it quick. It was basically a solution that was an outcome of the Christchurch earthquakes that we had in the earlier decade. And basically they had a lot of foundation rebuilds to do and very poor ground conditions. And this timber solution was a cost-effective way to meet that demand.
Great. Yeah, thank you. I think it's very innovative.
Did the cathedral get rebuilt?
Not yet. Takes a long time down here.
Not like Notre Dame.
Thank you very much.
Cheers, guys.
Great. Thank you so much.
Thank you.
Bye.
Last up, we have Monash University.
Hi, I'll just share screen.
There we go. We can see your presentation. Thank you very much. Please begin.
Okay. So I'm Raj, and I'm joined today by Sophia, Nipani, and Jane, and we'll be presenting Humming Home, which is Monash University's submission into new housing division for the competition. We are Monash Sustainable Buildings. We're a team of engineering students studying many different specializations, as well as other degrees such as commerce, architecture, and law. As a whole, our team aims to be a net positive to our community, which is why we've decided to design a domestic violence transition home. Originally, this house was designed for the 2023 Build Challenge, but due to complications, we are submitting this as part of the design challenge instead. I'll pass now to Jane, who will talk through our narrative and context.
Thanks, Raj. So Raj mentioned that we are building a transition home. So what is it exactly? Transition home built for domestic violence survivors for temporary housing to bring back sense of normalcy for them. It is an issue that is important to us because in Victoria, family violence is the leading cause of homelessness for women and children. Having home primary target market are women and children, and we also consulted to Cara House and Lighthouse Foundation, which are an organization that works with domestic violence survivors. They said that there are scarcity of transition home right now, and we also discussed with domestic violence survivor, and they said that there are lack of security and storage on the house. I'll pass to Nipuni for design goals.
Thanks, Jane. So some of our primary design goals are listed on the screen, with recovery, sense of security, and privacy being chosen to cater for the needs of occupants, and climate resilience, scalability, durability, and addressing the overarching issues related to scarcity of housing and climate disaster. To give the occupants the best opportunity to get back on their feet, we have carefully selected a site that is located in an area with a low crime rate, low property prices compared to the rest of Melbourne, as well as one that provides ample access to amenities such as garden space, easy access to transport, shops, and hospitals. It is, however, also located among many trees in a zone that is classified as high to very high risk for bushfires, so the house is being designed to optimize against bushfire resilience as well. To assess the feasibility of the site, members of our team conducted a site visit and found that there is a steep incline from the front to the back of the site, with the slope confirmed to be 1 to 6 at its steepest point. We view this as big advantages, however, due to it increasing privacy as well as maximizing solar access. I'll now hand over to Raj to talk more on the design.
Thanks, Nipuni. So looking at the design in our floor plan, so we've designed a 1.5 bedroom house that is also designed for flexibility of the kinds of spaces the occupants can be in. So the half bedroom that I mentioned is the bed nook, which is central to the house. It can be opened up to be an extension of the living area, or it can be closed off to act as a small bedroom for a child. So that allows the occupants to either be a single woman or it could be a single mother with children. As for flexibility of the spaces, we want to have flexibility in having spaces that go from completely public to private. So when you enter the site to when you're with the collection of the multiple properties on the site to once you're inside the house, there's a good spectrum of public to private, allowing occupants to choose what kind of space they're in for their own comfort. I'll now pass over to Sophia for the lighting.
Thanks, Raj. We have conducted thorough research which has established a clear link between well-being, both physical and mental, and the optimization of lighting in a home. As a result, Humming Home has decided to implement Philip Hughes' ecosystem range of products which focus on ambience, mood, and optimization of tasks. Secondly, due to the nature of our site, as Nipuni mentioned earlier, we are looking to implement local climate considerations. These include designing against ember attacks by minimizing access points through joints and connections, which are weak points in the structure when exposed to fire, implementing fire-resistant materials such as DuraPanel in the interior of the home and an MGO board along the exterior, creating outer barriers to separate the home and the surrounding areas as much as possible through trenches, high moisture content plants, and fence. And also a critical aspect of our design has been creating an escape route, which is shown on this slide here and highlighted in red and is through the windows and doors. I'll now pass back to Raj.
Thanks, Sophia. So we've been consulting our National Construction Code and to make sure that we're complying with all the local building regulations. You can see on screen in the bottom right, there are some sections that we've put on there that are relevant to our house. As for how our house actually sits within those building code constraints, we're in climate zone 7 and of building class 1B. So now looking at some of the more technical aspects of our design, we've been doing a full life cycle analysis of our design of all our materials. From our research, the average European house has a embodied carbon emissions of around 600 kilograms of carbon per cubic meter. We've managed to get our house to just under 200. When considering that our materials can be recycled and reused as well, we can bring that down to 113.5 kilograms of CO2 per meter cubed per meter cubed. As for our energy modeling, we've been primarily using Design Builder due to its accuracy and ability to go in depth with the analysis. After a few iterations, and we've managed to sit at a EUI score of 34.47 kilowatt hours per meter squared annually. That translates to about 3 BTUs per square foot annually. We've also been using REM rate. So we've managed to get a Hertz index of about 44. And all of our energy modeling so far has been done without considering photovoltaics. In future, we will be incorporating photovoltaics into the design, so that will improve things. We have talked a bit about including a battery, but that's still something that we are deciding. I'll pass now to Jane for our systems.
Thanks, Raj. So our HVAC and hot water system are selected to ensure that they have an appropriate capacity for the size of the house, as well as having high efficiency and lower impact refrigerants. We also have made a plan for our ventilation system to ensure pollutants are removed from the kitchen and bathroom, as well as ensuring that there is an adequate supply of fresh air. Our other appliances have also been selected for efficiency and capacity, as well as water efficiency and ability to load shift. I'll now pass back to Raj.
Thanks, Jane. So just wrapping up now, we've already got an idea of what we'd like to be doing post semi-final, how long each task will take, and who will be doing them. So just to call out a couple of the design features that we'd like to be pursuing after this, we'd like to look at passive water treatment, especially given the size of our site. We'd also like to look into designing our construction joints for disassembly, because that will help with our life cycle analysis and our argument for scalability. That wraps up our presentation. Thank you for listening.
Thank you very much, students from Monash. Jurors, yes, can you stop sharing your slides and let's talk to the jurors.
On your write-up, you have a 6 kilowatt system on a 500 square foot house, which seems a little big.
Yeah, that was a mistake on our part. That's a carryover from the build challenge, because the build challenge required that as part of their rules.
Oh, okay.
But since then we haven't been considering PV. We will be considering that going forward.
Yeah, just I think the mission of the project is very admirable. It seems like this could be very replicatable. It's a small size, so I could imagine these could be built fairly quickly. And you just mentioned design for disassembly. So disassembly is at the end of the life. Are you thinking any sort of particular construction method for the new construction in terms of deployability?
Yes, so there's a few features for design for disassembly that we've actually been looking into, and more reasons than just the environmental aspects of it. So we've actually talked to Cara House, which is an organization that houses domestic violence victims. One of the things that they said is that durability is really a huge part of the houses that really needs to be considered. So designing the house for disassembly really allows like parts of the house to be replaced. But at the same time, in terms of designing for disassembly from an environmental standpoint, we're looking primarily at the joints using bolts, but also using materials that can be recycled and reused. The house can also, we're trying to see if we can make the house relocatable as well. So given the small size, that helps, but also we're not using concrete foundations. We'll be using a system called shorefoot footings, which is essentially these steel footings with 4 poles that stick into the ground. And that's been used in a lot of projects in Australia, and it has minimal ground impact. So that's one of the areas that we're looking into as well.
Yes, I think highlighting some of those things of the pin foundations and I think those could be some of the things that you take further.
I think that's wonderful that you're adding the sensory part to the design and helping a group that needs it. And it's just very beautiful that you're adding that component into the home.
Yes, I guess like our main thing was like about occupant recovery. So we wanted to capitalize on all the senses as much as possible.
Is it really $300 a square foot because it's so small, or?
$300 a square foot.
You had $160,000 to build it, and 500 square feet is about $300 a square foot.
Oh, right. Okay. So at the moment, our costs are mainly for material costs. They haven't considered all the other considerations. Like I think we've included actual construction costs as well. But there are certain costs like cost of land and other things like that that we haven't included as well. So that price probably is a bit small.
Small? 300 is a lot.
There's
So
also
our-
probably a currency conversion.
No,
Yeah.
and you have it in both currencies, 236,000 in Aussie dollars, but only 160 in US.
Well,
160, okay.
could I maybe pass to Sophia?
Not too sure. It's okay. That's quick.
Sorry.
Sorry.
I love the 1.5 bedroom thing. I've never seen that before. That's adorable.
Yeah,
Is it-
like in homes in Australia, sometimes like that's like you can kind of have like a space which can be either like a study area or converted into a bedroom, and it's quite like flexible, especially in like smaller homes because yeah, as you said, it's only 50 meters squared. So and what Raj was saying before, by making it so small, there's more of like a scalability aspect. So the idea is that we can then replicate multiple houses on one lot. And if this was something that we wanted to present to like a local council as an initiative for them to take up, it's more doable in a way, as you say, because it's not like a 3-bedroom home. But yeah, this 1.5 bedroom thing is like, it can be a study space, it can be a bedroom, it can just be a place where they can enjoy, recover, and that was the thinking behind that idea.
Nice.
Well, thank you very much. That concludes our presentations for today.
Great, nice
you for
job.
having
Thank
us.
you.
We will return at 10 a.m. Eastern time tomorrow. That's 2 hours earlier than today began. And we'll have more presentations then. Thank you all students for all of your hard work. These have been great presentations, and we're looking forward to seeing the next ones.
Thank you all.
Thank you.
Thank you.
Thank you.
Thank you so much.
Do you need us anymore? Are we good?
You're good. We'll
Okay.
see you tomorrow.
Okie doke. Thanks.
Great, thanks, Caitlin.
Thank you so much, Sue and Sam.
You're welcome. Bye.
You guys have been wonderful.